Hello there, and welcome to Science for Sleep, where curiosity finds comfort and the cosmos takes its time to tell its stories. Tonight's slow drift through space begins not in a rocket or a lab, but right where you are now, maybe in bed, maybe resting after a long day, eyes half closed and thoughts wandering somewhere between stars and dreams. We're going to explore something that sounds simple at first, but the more you look at it, the stranger it becomes. Because right now, as you listen, as you breathe, as your planet quietly turns through the night, you're floating inside a bubble. A real one. Not a metaphor, not a science fiction idea, but a vast, invisible bubble made of gas, light, and time itself, surrounding our solar system like a delicate shell adrift in the Milky Way. It's not a thing we can see when we look up. The stars don't shimmer any differently because of it, and the moon doesn't cast a softer glow. Yet, every single one of us lives entirely inside it, wrapped in its faint, warm traces, carried along as the sun moves through space. Scientists call it the local bubble, and it's one of the most quietly astonishing facts about where we live. The Milky Way is full of swirling gas and clouds of dust, but we just happen to sit in an almost empty pocket carved out millions of years ago by exploding stars. It's as if our whole neighbourhood exists inside the afterimage of a cosmic event so ancient that everything we know has been shaped by its echo. But before we drift too far into the deep, I'd like to ask something small and grounding. Where are you listening from tonight? Maybe it's early morning and the light is just beginning to show. Maybe it's dark outside and all you hear is the steady sound of your own breath. Wherever you are, try to picture it. Your house, your town, your continent. Then the blue curve of the Earth, floating quietly in the black. Keep zooming out until the moon is just a pearl, until the sun becomes a dot among billions, until the Milky Way itself arches like a pale river of light. And somewhere in that vast sweep, there's a thin, shimmering pocket, a cavity of gas about 1,000 light-years wide. That's home. That's where we are, tucked into a glowing void in the fabric of our galaxy. If that image feels strangely soothing, like being wrapped in something ancient and vast, you're not alone. I find that too. And if you enjoy this slow kind of wandering, where science moves at the same pace as a heartbeat, you might like to give this video a quiet like or maybe subscribe, so we can keep travelling through space together, one calm story at a time. Now, settle in. Let's let the noise of the day drift away for a while and follow this idea gently where it leads. Because if we're going to talk about the local bubble, we need to understand what space around us is actually made of. And it turns out it's not nothing. It's never nothing. When we picture space, it's easy to think of it as completely empty. Just darkness. A perfect vacuum stretching forever. But the reality is softer and more complicated. Between the stars lies what astronomers call the interstellar medium, a thin mixture of gas, dust, and invisible fields. It's unimaginably sparse. A cubic centimetre of this space might contain just a single atom or two, and yet across the galaxy, it adds up to enormous structures. Clouds, filaments, and gaps shape the Milky Way like weather patterns in slow motion. Over millions of years, stars form from these clouds, live their brilliant lives, and eventually die, sending shockwaves through the medium, stirring it up again. It's a constant cycle of creation and clearing, dense and thin, light and dark. The solar system happens to be drifting through one of the thinner, more transparent regions of this galactic landscape. If we could see in ultraviolet or X-rays, the space around us would glow faintly, like a candle seen through fog. That faint light is part of the story. It's the whisper of what happened long ago when the local bubble was born. But before getting there, imagine what it would mean if we weren't inside this emptiness. If instead, the sun was surrounded by thick, cold clouds of interstellar gas, blocking much of the outside light. The night sky might look different. Starlight might shimmer less sharply. Even cosmic rays and particles reaching Earth would behave differently. In a way, the environment beyond our atmosphere, that vast invisible bubble, helps shape everything from the behaviour of the solar wind to the way our planet is shielded from certain cosmic influences. When scientists first suspected there was something unusual about our local region, it wasn't because they could see the bubble directly. It was because they couldn't. They noticed that light from nearby stars wasn't being scattered or absorbed the way it should have been if dense clouds filled the space between. Something was missing: gas, dust, the usual galactic fog. And that absence became a clue. By mapping out how starlight dimmed and reddened as it passed through space, astronomers realised that the Sun sits inside a surprisingly clear, low-density region, about 1,000 light-years across, surrounded by denser gas like a shell. That discovery unfolded slowly, over decades. In the 1970s and 80s, astronomers using X-ray and ultraviolet data started noticing faint emissions that didn't quite fit the picture of an ordinary local environment. It was as if there was a soft background glow coming from all directions, suggesting that the space around us was hotter and thinner than expected. Hot gas at temperatures of 1,000,000 degrees doesn't show up as visible light. It radiates in X-rays. Those early observations hinted that the region we inhabit might be filled with such hot plasma, the leftover breath of ancient supernova explosions. It's a strange thought. Every atom around us, even the ones floating between stars, has a history. The hydrogen in interstellar space was born in the Big Bang, more than 13 billion years ago. The heavier elements, oxygen, carbon, iron, were forged inside stars and scattered when they died. The local bubble, according to current understanding, is a direct consequence of that scattering. Roughly 10 to 15 million years ago, a chain of massive stars exploded one after another, each pushing the surrounding gas outward, carving out a growing cavity in the galactic medium. Over time, the overlapping shockwaves merged, hollowing out a vast region, our bubble, leaving its interior filled with thin, hot gas and its edges compressed into dense clouds. The result is almost like a fossil of stellar violence. The Sun just happens to be passing through it, like a ship sailing into the calm eye of a long-dissipated storm. It's not static either. The solar system is moving, about 230 kilometers per second around the galactic center, and the bubble itself isn't fixed. The edges shift and drift as gravity, radiation, and nearby star formation reshape the interstellar landscape. What makes this idea even more quietly beautiful is how everything we know about it had to be pieced together from the faintest hints. You can't point a telescope and see the edge of the local bubble the way you might see the rim of a crater. You infer its boundaries from data, from how certain wavelengths of light are absorbed, from the distribution of a neutral hydrogen, from the way dust glows when hit by starlight. It's like mapping a fog bank from the echoes of distant bells. Over time, astronomers began to realize that the local bubble wasn't unique. The galaxy is full of them. Interlocking cavities of hot gas formed by past supernovae, merging and colliding in slow, intricate ways. The Milky Way, in some sense, is a sponge of bubbles within bubbles, their boundaries forming the sites of new stars. And that brings us back to our quiet home inside the cosmic void. The local bubble is estimated to be roughly 1,000 light-years across, and perhaps 600 light-years tall. To put that in perspective, light, the fastest thing there is, would take a millennium to cross it. The Sun, in its galactic orbit, moves about 1 light-year every few tens of thousands of years, so our journey through the bubble spans millions of years. The edges of the cavity are not uniform. In some directions they're closer, in others, farther away. Where the bubble meets denser clouds, stars are still forming, like those in the Taurus and Perseus regions. In a way, we live in the hollow left behind by dead stars, surrounded by the birthplaces of new ones. It's a poetic kind of symmetry, though we'll resist the temptation to make it sound mystical. This is physics on a grand scale. The supernovae that carved this space weren't gentle. Each one released more energy in seconds than our Sun will produce in its entire lifetime. Their shockwaves heated and swept up interstellar gas, compressing it into shells hundreds of light years thick. Those shells, where pressure built up, later cooled and collapsed, forming new clouds and eventually new stars. Our bubble isn't just an absence. It's part of a long, ongoing process of renewal. Imagine it this way. You're in the middle of a quiet lake at night, and a long time ago someone dropped a series of heavy stones into the water. The ripples spread, collided, and merged, leaving calm water where they overlapped, but waves still rolling out at the edges. We're in that calm zone now, surrounded by the remnants of ancient ripples still shaping the shoreline. The stones, in this case, were stars, and their ripples were shockwaves expanding through the galaxy's thin gas. Of course, it took more than imagination to confirm any of this. Over the past few decades, missions like Gaia have provided precise maps of stellar distances and positions, allowing astronomers to trace the outlines of the local bubble in 3 dimensions. By comparing the locations of interstellar dust clouds to the distribution of young stars, they found that many of the nearest star-forming regions sit exactly on the bubble's boundary. It's as though the bubble's edge itself helped trigger the birth of those stars, the compressed gas at its rim collapsing under its own gravity to ignite new suns. Which means that when you look up at certain constellations, Orion, Taurus, Perseus, you're seeing stars that may owe their existence to the same ancient explosions that hollowed out the space we now inhabit. The violence of the past set the stage for the calm of the present. That's one of the quiet themes running through much of astrophysics. What seems serene is often the product of chaos slowed by time. The peaceful glow of a nebula hides the remains of collisions and implosions. The empty space we drift through was once the site of fire beyond comprehension. And in between those extremes there's us, fragile creatures building stories out of what remains. As our sun continues its orbit through the galaxy, it will eventually drift out of the local bubble, probably in a few million years, into another region with different densities and compositions. Nothing dramatic will happen. It's a slow transition, more like passing through changing weather than crossing a border. But the cosmic neighbourhood will change. The shielding effects of interstellar material, the properties of cosmic rays, even the shape of the heliosphere, the bubble created by the solar wind, all depend on the conditions of the surrounding interstellar medium. Right now, that medium is unusually thin and hot, which allows the solar wind to extend farther, giving our system a generous protective envelope. In denser regions, that envelope would shrink. So, in a subtle way, the local bubble contributes to the environment that shelters Earth and everything on it. We live, quite literally, inside a shield left behind by long-dead stars. It's humbling to think that the atoms in your body were forged in stars, but it's equally humbling to realise that the space around you, the very emptiness between those atoms, is shaped by stellar deaths too. Every breath you take is made of recycled material. Every radio signal, every beam of light we send into the cosmos travels through the ghost of ancient supernovae. If you step outside on a clear night and look toward the Milky Way, it's easy to feel small. But small doesn't mean insignificant. In fact, smallness can be a kind of connection. The same processes that shaped galaxies shaped us. The same physics that carves out cosmic bubbles governs the cells in your body. There's no separation, just scale. And somewhere in that thought, the night begins to feel softer again. The hum of distant traffic becomes the murmur of cosmic background. The space between seconds stretches a little. We're floating in a quiet pocket of the galaxy, surrounded by the aftermath of explosions, breathing air that once belonged to stars, moving slowly, peacefully through an ancient glowing void. The space around us seems so vast and silent that it's easy to imagine nothing at all lies between the stars, just black emptiness stretching forever. But space, even in its quietest reaches, is full of texture. It's filled with invisible matter and light, the faint breath of long-dead stars, a haze so thin that entire clouds of it would fit inside a single teaspoon if you could compress them down. This is the material that makes up what astronomers call the interstellar medium. It's not empty, it's simply delicate, so sparse that a cubic centimetre contains only a few atoms, yet so extensive that those few atoms multiplied over light years form great structures, ribbons of gas, sheets of dust, voids of nearly perfect clarity. And within that faint landscape lies the bubble we call home. If you could see the Milky Way not as a band of stars but as a living map of gas and dust, you'd notice it isn't smooth. It's mottled like the surface of foam, with patches where star-forming clouds are thick and others where something has cleared them away. The Sun and its planets happen to sit inside one of those cleared-out patches, a cavity about 1,000 light-years across. The edges of it glow faintly in wavelengths our eyes can't detect, soft X-rays and ultraviolet light marking where the empty space meets denser regions of gas. The interior, where we drift, is almost empty by cosmic standards, a volume scoured clean by violence long past. From the inside, though, there's nothing to see. The shell is too far away, too transparent. We can only know it's there by the way it touches light. Astronomers first suspected that something strange surrounded the solar system when they noticed a mismatch between what theory predicted and what telescopes revealed. Light from nearby stars was passing through space with less interference than expected. Normally, dust and gas absorb and scatter starlight, making distant stars appear redder and dimmer. But stars within a few hundred light-years of the Sun were unusually bright and unreddened. There was less material between us and them than models allowed. The simplest explanation was that we were inside an unusually low-density pocket of space. Later, when X-ray satellites detected a faint diffuse glow coming from all directions, the picture began to take shape. The glow suggested that the empty region wasn't cold but hot, so hot that atoms were stripped of their electrons, forming plasma at temperatures of 1,000,000 degrees. That kind of heat doesn't happen quietly. It's the fingerprint of explosions. The story that followed reached back 10 or 15 million years to a time when our part of the galaxy was busier. Clusters of massive stars lived and died nearby, each one lasting only a few million years before collapsing and detonating as a supernova. Every explosion blasted gas outward, sweeping up the interstellar medium and piling it into expanding shells. As these shells overlapped, they carved out a common cavity, merging into what would become the local bubble. The Sun wasn't here yet. It would drift in later, born somewhere else along the galactic arm. What those long-gone stars left behind was an enormous, irregular void, bounded by walls of compressed gas and dust, a bubble so large that hundreds of thousands of stars now sit along its rim. To imagine what that means, picture the galaxy as an ocean filled with invisible mist. The shockwaves from supernovae act like waves crashing outward, clearing fog and stirring currents. Where several waves meet, the mist is pushed aside, leaving behind pockets of clear water surrounded by denser regions. Our solar system floats in one of those pockets. The walls are uneven, some closer, some farther. In certain directions, the bubble opens into neighbouring cavities, connecting like tunnels in a sponge. In others, dense molecular clouds press against its boundary. These are the birthplaces of new stars, areas like Taurus, Perseus, and Ophiuchus. Their existence isn't coincidence. When the edges of a supernova bubble compress nearby gas, gravity eventually takes over, collapsing it into knots that ignite. So the same chain of explosions that once hollowed out our surroundings may also have sparked the creation of new suns at its periphery. The edges of the bubble aren't smooth or solid. They're more like filaments of folded tissue. If you could travel there, which would take longer than all of human history many times over, you'd find clouds cold enough for molecules to form, thin enough that you could still see the stars beyond, but dense enough to glow faintly in radio and infrared light. That is where the remnants of the shockwaves still linger, cooling and fragmenting into new structures. Within those regions, dust grains coated with ice drift through ultraviolet starlight, chemical reactions slowly building complex molecules. Every carbon atom, every trace of oxygen or nitrogen in your body pass through places like that before being incorporated into planets and people. The shell that surrounds us is not just a boundary, it's part of the galaxy's recycling system, a membrane between destruction and creation. Inside the bubble, conditions are unusually gentle. The density of interstellar gas is about 1/10 of what it is in denser clouds. That means fewer cosmic particles collide with the heliosphere, the protective bubble formed by the solar wind. Our sun's outflow of charged particles pushes back against the thin surrounding medium, creating a region that stretches far beyond Pluto. In a denser environment, that shield would shrink. In this spacious void, it expands freely. Some scientists think this has helped stabilize the conditions around Earth over geological timescales, reducing the flux of high-energy cosmic rays that reach the planet's surface. If true, the local bubble isn't just a curiosity. It may be one of the quiet contributors to the environment that allows life here to persist. Still, the bubble isn't permanent. It's part of a dynamic system that changes over millions of years. Our sun moves around the galaxy at roughly 200 kilometers per second, completing one orbit every 230 million years. On that journey, it drifts in and out of different environments. Sometime in the distant future, the solar system will leave this cavity and enter another region of the interstellar medium. The boundary won't be sharp. It will be like moving from one kind of weather to another, but it will change how far the solar wind reaches, how cosmic radiation behaves, perhaps even how interstellar dust interacts with the outer planets. Right now, we happen to be in a calm patch, a kind of cosmic clearing, the result of ancient storms we never saw. Discovering this structure in detail took patience. Observatories like the European Space Agency's Gaia mission have mapped the positions of more than 1 billion stars with extraordinary precision, allowing researchers to build 3-dimensional charts of the local interstellar medium. By measuring how starlight is absorbed by dust at different distances, they've traced the outlines of the local bubble and its neighbours. When these maps are combined with data from X-ray telescopes and radio surveys, a picture emerges of a complex interconnected web. The local bubble touches others. The loopy bubble near the Scorpius-Centaurus region, the North Polar Spur extending above the galactic plane, smaller cavities linking them like corridors. The galaxy, seen this way, looks less like a disk and more like a sponge, full of cells and tunnels carved by generations of dying stars. In the middle of all this, the solar system's position is almost perfectly central, not by design, just by chance. The Sun entered the bubble a few million years ago, and calculations suggest it's still travelling through its interior. In another few million years, it may reach the far side and move into one of the adjacent cavities. That slow migration is typical. Stars wander through the interstellar medium, weaving paths through the complex network of clouds and voids. Each region they pass through leaves subtle marks on their surrounding planetary systems, influencing the size of their heliospheres, the intensity of cosmic radiation, and the flow of interstellar dust. The invisible shell around home is therefore more than scenery. It's part of the long, quiet dialogue between stars and space. Every supernova that once erupted nearby sent out material that would one day become part of new stars, planets, and perhaps life itself. The hot, thin gas filling the bubble still carries the trace elements from those explosions: iron, oxygen, neon, diluted but present. The same atoms once accelerated outward at thousands of kilometers per second are now drifting gently, waiting for the next cycle to begin. Eventually, as the bubble cools and collapses, it will mix again with the surrounding medium, and some future cluster of stars may form from that material. In that sense, the local bubble is not just a structure, but a phase in the galaxy's breathing, an inhalation that began with destruction and will end with creation. If you could somehow stand outside it and look back, the bubble would appear as a dim, irregular glow against the backdrop of the Milky Way, a hollow filled with faintly luminous plasma. The Sun would be a small dot near its centre, surrounded by the orbits of the planets like concentric ripples. Around that, an ocean of near vacuum stretching to the walls of compressed gas. Beyond those walls, the thick molecular clouds where stars are born. The scale defies ordinary imagination. Even the smallest variations in density within the bubble span distances greater than the entire solar system. Yet this immense emptiness affects the thin veil of particles that reach us every moment. It shapes the background radiation our instruments detect. It defines the cosmic neighbourhood through which our probes travel. When Voyager 1 and 2 left the heliosphere and entered interstellar space, they didn't cross into pure nothingness. They crossed into the material of the local bubble. The readings they send back, measurements of plasma density, magnetic fields and cosmic rays, are our first direct taste of the medium that fills this cavity. Those tiny signals, picked up decades after launch, confirm that the space beyond the Sun's influence is still part of the vast hot interior left behind by ancient explosions. The Voyagers are our slowest messengers, drifting through a region that took millions of years to form and will last millions more. They are, in a quiet way, our first travellers within the bubble itself. There's something oddly comforting about that thought. For all the violence that created this place, what remains is peace, an expanse of gentle radiation and rarefied gas through which we move without even noticing. We exist inside the cooled memory of supernovae, the byproduct of energies beyond measure. The walls that once roared with shockwaves are now nurseries for new light. The boundary that once marked destruction now shelters creation. And inside it all, here we are, listening, resting, letting the universe tell its slower stories. If you could look at the Milky Way not as a ribbon of light scattered across the night sky, but as it truly is, a vast rotating disk of stars and dust stretching more than 100,000 light-years, you would see that it's anything but uniform. From a distance, it might seem smooth and luminous, a spiral of steady brightness, but inside, the structure is more like a weather system than a solid body. The galaxy is filled with clouds, filaments, and empty patches, all moving and changing over millions of years. These aren't clouds like the ones we see above our heads. They're made of gas and dust so thin that you could fly a spacecraft through one and never notice. Yet collectively, they hold enough mass to build stars, planets, and everything that has ever shone in the dark. Between these clouds lie gaps, regions where shockwaves or stellar winds have swept the space nearly clear. The Milky Way is a patchwork of density and emptiness, a living mosaic of creation and destruction. This space between stars, which might seem like a void, is more like the ocean between islands. It has currents, tides, and storms, all governed by magnetic fields, radiation, and gravity. Within that ocean, the interstellar medium divides itself into several phases, each with its own temperature, pressure, and density. There's the cold molecular gas, where temperatures drop close to absolute zero and atoms stick together to form molecules: hydrogen, carbon monoxide, water, ammonia. These regions are the darkest and densest parts of the galaxy, and it's within them that new stars are born. When gravity pulls enough material together, the gas collapses, heats up, and ignites into light. Surrounding those molecular clouds are layers of warmer, more diffuse hydrogen, a sort of middle ground where atoms drift freely. Beyond that lies an even hotter, thinner component: ionized plasma heated by shockwaves and radiation from massive stars. All these phases coexist, blending into one another, constantly cycling as stars form, shine, and die. Our solar system right now happens to sit in one of the emptiest phases, the hot, thin gas of the local bubble, but it wasn't always there. Over the past few million years, as the Sun has orbited the centre of the galaxy, It's passed through denser regions and thinner ones, clouds and gaps like a traveller moving through different kinds of weather. Those transitions happen slowly. A single trip through one interstellar cloud might last hundreds of thousands of years. To us, it seems static, but on galactic timescales, the sun is always on the move, crossing invisible boundaries that shape the conditions around it. To get a sense of what these galactic clouds look like, imagine a nebula, the Orion Nebula, for instance, where newborn stars light up the gas around them. It's colourful in photographs because telescopes capture wavelengths of light invisible to the human eye, mapping hydrogen in red, oxygen in green, sulfur in blue. The real colours would be faint, almost imperceptible. Still, what you'd see is a structure full of folds and filaments, regions where gas is dense enough to glow and others where it thins into shadow. Now stretch that pattern across thousands of light years, layer upon layer, and you begin to picture what the Milky Way's disk looks like when seen through instruments that can peer into its hidden depths. It's not a smooth spiral, but a complex web of filaments connected by vast cavities. The local bubble is one of those cavities, and it connects to others through narrow tunnels, forming a network of voids and walls like the spaces between soap bubbles in foam. Astronomers map these structures by studying how starlight changes as it travels through them. Every atom and molecule absorbs and emits light at specific wavelengths. By splitting the light from distant stars into spectra, scientists can see which wavelengths are missing and identify what lies between. Hydrogen leaves one kind of signature, sodium another, calcium yet another. Dust adds its own effects, dimming and reddening the light. By comparing spectra from many stars at different distances, astronomers can reconstruct the three-dimensional distribution of gas and dust around us. The resulting picture is always in motion. Supernovae carve new holes, stellar winds from young clusters clear channels, and fresh molecular clouds condense along the edges. The galaxy is constantly rearranging itself, like weather shifting over continents. The emptiness we inhabit was once dense too. Long ago, perhaps tens of millions of years back, the region where the solar system now drifts was part of an active star-forming zone. A cluster of massive stars lived and died here, their lives brief and brilliant. Each one, as it burned through its fuel, sent out fierce winds that pushed away nearby gas. When they exploded, their shockwaves overlapped, sweeping the area clean. The result was the local bubble, a kind of cavity surrounded by compressed shells. Along those shells, the next generation of stars began to form. It's a pattern seen throughout the galaxy. Stars die, clear out space, and trigger the birth of new ones in the surrounding gas. Over time, the dense regions thin, the thin regions fill, and the cycle continues. The Milky Way, like a living organism, constantly breathes in and out, drawing matter into stars and exhaling it back into space. If we could see this breathing on a timescale of millions of years, the galaxy would look alive, its spiral arms rippling with waves of density that move slower than anything we can directly witness. These waves, called spiral density waves, are areas where stars and gas crowd together temporarily, as they orbit the galactic centre. As material enters one of these waves, it compresses and forms stars. As it leaves, it drifts apart again. Between the arms, the density drops. The Sun is currently between two of these arms, in a relatively calm region often referred to as the Orion Cygnus Spur. That's part of why the night sky looks as it does, rich with stars but not obscured by thick dust clouds. If we were deeper inside a spiral arm, the sky would glow with bright nebulae, but many stars beyond would be hidden behind curtains of gas. Even within this quieter zone, there are smaller pockets of activity. Near the edges of the local bubble, dense molecular clouds like Taurus and Perseus are forming stars right now. Their positions mark where the bubble's expansion once compressed gas into new clusters. It's a reminder that what seems static is really a conversation between forces: pressure, gravity and time. The balance between them shapes everything from the smallest dust grain to the largest galactic structure. The Sun, Earth, and all of us move within that dialogue, products of its history and participants in its ongoing flow. The texture of the galaxy becomes clearer when viewed across different wavelengths of light. In radio maps, cold hydrogen traces sprawling arms that wrap around the Milky Way's disk. In infrared, warm dust glows softly, revealing where stars are forming. In X-rays, hot gas outlines the cavities carved by ancient explosions. Together, these observations show a galaxy made of contrasts: cold and hot, dark and bright, dense and empty. The boundaries between them aren't sharp. Instead, they blend like gradients of temperature and pressure in a planetary atmosphere. The interstellar medium is a continuum, not a set of separate boxes, and the local bubble is just one transient feature within it. Over millions of years, it will cool and refill with gas, while new bubbles will form elsewhere. The structure we live in today is just a momentary pattern in the larger flow. One of the striking insights from recent research is how interconnected these patterns are. The local bubble is not an isolated void. It connects to others through channels of low-density gas, forming a labyrinth that winds through the galactic plane. Astronomers have identified neighbouring cavities such as the Loop 1 bubble and the superbubbles around Scorpius and Centaurus, each formed by multiple supernovae. These cavities sometimes overlap, creating bridges where the boundaries merge. In those places, gas from one region flows into another, balancing pressure and mixing elements. Over time, the entire interstellar medium becomes a network of expanding and collapsing bubbles, their walls glowing faintly where they meet. The galaxy's large-scale structure depends on this constant churning, a balance between the energy injected by dying stars and the cooling processes that let gas condense again. From our perspective on Earth, it's difficult to grasp these scales. A single light year, the distance light travels in 1 year, is nearly 10 trillion kilometers. The local bubble stretches across 1,000 of those. A molecular cloud might span 50 light years, a supernova remnant 100. Yet all of this, vast as it is, fits inside a single spiral arm of the Milky Way. The entire galaxy contains hundreds of billions of stars, and beyond it lie billions of other galaxies, each with its own intricate network of clouds and gaps. The local bubble, then, is both enormous and tiny. Enormous to us, tiny to the universe. Even so, its existence influences what we see and how we see it. Because the bubble is relatively empty, starlight from within and beyond passes through with little absorption. That clarity allows us to observe distant stars and nebulae more easily than if we were inside a denser cloud. It's as if our cosmic neighbourhood provides a natural window through the galaxy. The transparency of the local interstellar medium has shaped astronomy itself. The instruments that detect faint X-rays, ultraviolet light, and radio waves all benefit from the low density of our surroundings. If we lived inside a thick molecular cloud, much of that radiation would be blocked or scattered, and the universe would appear far dimmer. The relationship between stars and their surroundings is reciprocal. Stars create the bubbles, and bubbles in turn shape where new stars can form. This feedback governs the evolution of galaxies. When many massive stars die in close succession, they can blow out large portions of a galactic disk, forming what astronomers call superbubbles. These structures can stretch thousands of light years and even vent material into the galactic halo, seeding the surrounding space with heavy elements. Over time, gravity pulls that material back down, enriching future generations of stars. The process keeps the galaxy chemically diverse. The oxygen you breathe, the calcium in your bones, the iron in your blood, all were forged in earlier generations of stars and spread by events like the ones that created the local bubble. The cycle continues endlessly. Formation, fusion, explosion, dispersal, condensation, and rebirth. When you lie beneath the night sky and see the faint arc of the Milky Way, You're seeing the bright concentration of stars within one of those arms, but you're also seeing through layers of gas and dust shaped by all this history. The dark lanes that split the band are dense clouds of cold material blocking light. The glowing patches are clusters of hot young stars burning through their birth clouds. Between them lie the gaps, cavities like ours, where the space has been cleared by stellar winds and explosions. Each pattern, each brightness, is a clue to the ongoing story of the galaxy breathing in and out. If human lives could stretch long enough to watch this process unfold, the sky itself would change. Constellations would drift, nebulae would expand or fade, clouds would shift. New stars would light up along the bubble's rim while others dimmed into remnants, but on our shorter timescales the sky appears still, an illusion born of our brief perspective. The structures of gas and dust that define our galactic environment move so slowly that they seem eternal. That illusion of permanence is comforting, even though it isn't true. The bubble we inhabit, the clarity that lets us see the stars, the patterns of clouds and gaps that shape our view, all are temporary. Still, for now, this arrangement serves as our window. It lets us peer out across light years, tracing the edges of the bubble and beyond, following the threads of gas that connect us to the wider Milky Way. It reminds us that emptiness and fullness, void and substance, coexist everywhere, each depending on the other. The galaxy isn't a solid disk of stars, but a dynamic environment, sculpted by energy and time, filled with clouds that give birth and gaps that give rest. And somewhere near the centre of one of those gaps drifts our small sun, surrounded by planets, all of it moving through the thin, hot air of a space once filled with fire. Long before our solar system drifted into the region it now calls home, the space we occupy was a very different place. It wasn't the open, airy cavity of low-density gas that surrounds us today, but a crowded stretch of galactic real estate filled with dust, hydrogen, and newly born stars. It was part of a busy neighbourhood near what astronomers call the Scorpius-Centaurus-Ob Association, a cluster of massive short-lived stars that formed together roughly 15 million years ago. Those stars, brilliant and enormous, burned through their fuel in only a few million years, living fast and dying spectacularly. When they reached the end of their lives, they didn't fade quietly. They exploded as supernovae, unleashing energy so intense it reshaped the structure of space itself. Each supernova was a cataclysm on a scale almost impossible to grasp. A single event released more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. The shockwaves from those explosions raced outward at thousands of kilometers per second, slamming into the interstellar medium, the thin soup of gas and dust filling the galaxy. When a shockwave passed through, it swept up that material like a broom, compressing it into dense shells and pushing it aside. The space behind the wave became hot and thin, filled with ionized gas glowing in ultraviolet and X-ray light. When several supernovae went off in roughly the same region, their shockwaves overlapped, merging into one another, carving out a single enormous cavity. That cavity is what we now call the local bubble. To picture what happened, imagine a series of overlapping ripples spreading across a pond. Each supernova sent out a spherical shell of energy, expanding through the interstellar medium. When those spheres collided, the overlapping regions intensified the clearing effect. The gas was swept up into dense ridges that marked the boundaries of the forming cavity. Over time, as more stars died, the cavity grew, stretching hundreds of light years in every direction. The edges cooled and condensed, forming the walls we see today, dense enough to birth new generations of stars. The interior remained filled with hot, low-density plasma, a remnant of the violence that created it. The first supernova in this chain likely occurred around 14 or 15 million years ago, near the centre of the Scorpius-Centaurus Association. The last few may have gone off as recently as 1 or 2 million years ago. Altogether, astronomers estimate that about 15 to 20 supernovae contributed to the formation of the local bubble. Their timing overlapped enough that the cavity never had a chance to cool or collapse completely. Each new explosion reheated and reinforced the existing structure, keeping it inflated like a balloon continually refreshed with bursts of air. Without those repeated blasts, the surrounding interstellar gas would have rushed back in under pressure, erasing the bubble within a few million years. The evidence for these ancient explosions comes from several sources. One is the distribution of radioactive isotopes found on Earth and in the seafloor. Layers of deep ocean sediment contain traces of iron-60, an isotope produced only in supernovae. Because it has a half-life of about 2.6 million years, any iron-60 detected today must have come from explosions that occurred within the last few million years and relatively nearby. Measurements of that isotope's abundance suggest that at least one supernova went off within a few hundred light-years of Earth, almost certainly one of the final blasts that contributed to the bubble's formation. Another line of evidence comes from stellar motion. By tracing the trajectories of stars in the Scorpio-Centaurus association backward through time, astronomers can reconstruct where they were millions of years ago. The paths of several subgroups converge near the centre of the local bubble, consistent with the idea that their most massive members exploded there. As those stars drifted apart, their combined explosions continued to sculpt the region, pushing gas outward and triggering star formation along the expanding shell. In fact, many of the nearest young stars to the Sun, those in regions like Taurus, Lupus and Ophiuchus, appear to have formed along that very boundary. The chain of death and birth is continuous. The deaths of one generation created the cradle for the next. Inside the bubble, the temperature of the gas remains extraordinarily high, on the order of 1 million kelvins. At such temperatures, atoms are stripped of their electrons, and the gas becomes plasma. Because the density is so low, only about 1 atom per 10 litres of space, this hot plasma doesn't radiate its energy quickly. It cools slowly, over millions of years. That's why the cavity still exists today. If it were denser, it would have collapsed long ago. Instead, the thinness preserves its heat and structure. In X-ray observations, this hot gas reveals itself as a diffuse background glow that pervades the sky, especially at higher galactic latitudes where the view isn't blocked by dense clouds. As dramatic as these events were, from the perspective of the galaxy, they were routine. Supernovae occur roughly once every 50 years somewhere in the Milky Way. Over billions of years, they've shaped the entire interstellar medium, injecting heavy elements and carving out cavities. The local bubble is simply one of countless others, yet for us, its particular history matters because our solar system now resides within it. The Sun wasn't born here. It likely formed in a different cloud about 5 billion years ago. Only a few million years ago did it wander into this cavity. Its entry point and trajectory happened to place it near the centre, giving us a front row seat to the lingering traces of those long ago explosions. You can think of this region as the ghost of a stellar nursery. The Scorpio-Centaurus association once held dozens of massive stars, each more than 10 times the mass of the Sun. These stars emitted intense ultraviolet radiation that sculpted the clouds around them even before they died. Their combined energy created bubbles within bubbles, a layered structure of hot plasma and compressed gas. When they finally exploded, the shockwaves merged those smaller cavities into one dominant one. Over the next few million years, as the shells collided, their boundaries cooled and became dense enough to collapse again under gravity. That collapse gave birth to the next generation of stars along the rim, some of which are still forming today. It's remarkable to consider how long the effects of a supernova last. The explosion itself is over in seconds. The visible afterglow might persist for thousands of years, fading as the shock wave expands. But the structural impact on the surrounding interstellar medium endures for tens of millions of years. The local bubble is a fossilized remnant of that process, still large enough to contain hundreds of thousands of ordinary stars. Its edges are dotted with young clusters whose origins can be traced to the compression of gas along the bubble's boundary. In a sense, the bubble is both a graveyard and a nursery, preserving the memory of stellar deaths while nurturing new life from their debris. When scientists model the formation of such cavities on computers, they find that the details depend on how the supernova overlap in time and space. If explosions occur too far apart, each creates its own smaller remnant that cools before merging with others. But if they occur close together, their shockwaves combine into a coherent superbubble that can grow to enormous size. The local bubble fits the latter pattern. The massive stars of Scorpius Centaurus were close enough that their supernova remnants merged, producing a single structure rather than a collection of smaller ones. The process wasn't symmetrical, though. The surrounding interstellar medium wasn't uniform, and so the expanding shockwaves met different resistance in different directions. That's why the bubble's shape is irregular, longer along some axes, narrower along others. The combined energy of 20 supernovae is staggering. Each released about 1044 joules, so together they injected roughly 2 Sustores 1045 joules into the local interstellar medium. That energy drove gas outward at hundreds of kilometers per second, clearing a volume now measuring about 1,000 light-years across. The mass of gas displaced by that process would be equivalent to tens of thousands of suns, yet the space inside the cavity remains hot enough to keep it inflated. Over time, as the plasma cools and the pressure drops, the walls will begin to drift inward, and the surrounding gas will slowly refill the void. But that process will take many millions of years, and long before it happens, the sun will have moved on. The traces of these explosions are still visible in the elements that make up our own planet. Every atom heavier than hydrogen or helium was forged in stars and scattered by events like these. The iron in the Earth's core, the oxygen we breathe, the calcium in our bones, all of it originated in stellar furnaces and was distributed by supernovae. The chain of events that built the local bubble is, in a roundabout way, part of our own ancestry. The cosmic blast that cleared the space we now inhabit also enriched the raw materials from which life eventually formed. The idea that we live inside the aftermath of multiple supernovae might sound alarming, but in reality it's one of the reasons our environment is so calm. The violent phase is long over. What remains is a zone of relative safety. The thin gas inside the bubble acts as a buffer between us and denser, more turbulent regions of the galaxy. The edges, where new stars form, are far enough away that their radiation doesn't reach us strongly. It's as if we're sitting in the quiet eye of a storm that has already passed. The energy that once roared through this space has dissipated into a gentle warmth spread across light years. Astronomers continue to refine the details of this story with better data. The Gaia mission has allowed them to trace the three-dimensional motion of thousands of nearby stars, creating a kind of time-lapse of the local region. By combining those motions with models of supernova expansion, they can reconstruct where and when each explosion likely occurred. The resulting maps show that the local bubble's boundaries correspond closely to the locations of nearby star-forming regions. That alignment strengthens the case that the bubble's formation directly triggered the birth of those young stars. In other words, the chain of cause and effect that began with the deaths of massive stars continues even now in the form of new light emerging along the edges. The picture that emerges is one of continual renewal. The same energy that destroys also creates. The Milky Way is not a static arrangement of stars, but a dynamic ecosystem. Supernovae act as both endings and beginnings, resetting the conditions of their surroundings and enriching the galaxy with heavy elements. Without them, there would be no iron cores in planets, no oxygen-rich atmospheres, no carbon-based life. The local bubble is a visible reminder of that balance. Its vast emptiness is not absence but aftermath, a quiet space maintained by the memory of fire. As our sun continues its slow orbit around the galactic center, it will eventually drift toward the bubble's edge and beyond. Perhaps in another few million years, it will enter a new region shaped by different explosions, different histories. The boundaries of these bubbles are always changing, merging and reforming. Each one marks a chapter in the galaxy's endless cycle of transformation. For now, we drift in the hollow left behind by stars that once lit up the night sky of this region, long before Earth even existed. The cosmic blast that built our bubble was part of a pattern stretching back to the beginning of the Milky Way, a pattern of energy passing from one generation of stars to the next, shaping the space between them and giving every corner of the galaxy its own unique texture. When the last of the great explosions faded, the galaxy fell back into silence. Not the kind of silence that comes instantly, but the slow, heavy stillness that settles after something enormous has ended. The shockwaves from those supernovae had spent their fury. The roaring fronts of energy had cooled into expanding shells of gas, and the chaos that once filled this stretch of the Milky Way began to unwind into calm. The local bubble, still hot and glowing faintly in invisible light, became a relic of that storm, a hollow of rarefied gas surrounded by denser clouds. Over millions of years it changed from a site of violence to one of balance, and inside it, long before the sun arrived, the quiet took hold. In those first few million years after the final supernova, the walls of the cavity kept drifting outward. The shockwaves, though slower now, continue to push against the interstellar medium, piling gas into the filaments that would become the edges of the bubble. The interior gas, still at 1,000,000 degrees, expanded gently, maintaining the cavity's size even as the galaxy's overall pressure tried to compress it again. Gradually the hot plasma began to cool. The atoms that had been stripped of their electrons started recombining. Radiation leaked away in the form of soft X-rays, fading into the background glow that astronomers detect today. The violence had burned itself out, and what remained was structure, an immense pocket of space defined by the memory of energy. The story of this cooling phase is written in the light that fills it. The faint X-ray background that pervades the sky, sometimes called the soft X-ray diffuse emission, is one of the signatures of the local bubble. When detectors first picked it up, scientists thought it might come from distant galaxies or from gas near the centre of the Milky Way. Only later did they realise much of it originates right here, in the space surrounding the solar system. That background is the whisper of the ancient storm, the faint glow of a hot gas still losing its heat after millions of years. It's astonishing to think that every photon in that glow has been travelling through space since long before humans existed, carrying the memory of a time when this region was filled with chaos. If you could somehow stand in the middle of that aftermath, not on a planet, not protected by an atmosphere, but drifting freely through the vacuum, you wouldn't see or hear anything at all. The gas is too thin to glow visibly. The temperature, though high in theory, would mean nothing to you. There are so few particles that you'd feel no heat. Space would appear empty, serene, indifferent. The quiet after the storm isn't an audible quiet, but a quiet of density, of motion slowed down to scales we can't perceive. The violence is gone, replaced by emptiness and equilibrium. That equilibrium has persisted for more than 10 million years, shaped by subtle forces. The hot gas inside the bubble exerts pressure on its surroundings, balancing against the weight of the denser interstellar medium outside. Gravity pulls gently on the walls, but magnetic fields running through the galaxy help stabilize them, threading the clouds like invisible wires. Occasionally, a nearby star's radiation or wind nudges the boundary, stirring it slightly, but overall the system remains stable. The bubble has become part of the galaxy's architecture, one of many cavities that together give the Milky Way its mottled texture. At some point during this long cooling period, the sun drifted into the scene. Our star, moving steadily along its orbit around the galactic centre, entered the bubble a few million years ago, probably through one of its thinner regions near the edge. As it did, the environment around the solar system changed. The density of the surrounding gas dropped dramatically. The solar wind, which is the stream of charged particles flowing outward from the sun, could expand farther without meeting resistance. That expansion created a vast protective bubble of its own, called the heliosphere, which now stretches well beyond Pluto. Inside that bubble, the solar wind dominates. Outside, the thin plasma of the local bubble resumes. The two structures nest like Russian dolls, our solar bubble inside the galactic one. The heliosphere and the local bubble interact in subtle ways. The pressure of the interstellar gas and magnetic fields outside helps shape the boundary of the heliosphere, influencing how cosmic rays enter our solar system. Because the local bubble is so sparse, the heliosphere can inflate to a larger size than it could in a denser region. This may have helped reduce the number of high-energy particles reaching Earth, offering a quiet stability that's lasted throughout human history. It's one of those coincidences that's easy to overlook, but may have had deep consequences. The calm we experience here, stable climate, manageable radiation levels, a sense that space is mostly empty, owes something to this cosmic lull. If we could speed up time and watch the bubble evolve like a film, we'd see that even in its quiet phase, it's not completely still. The walls slowly shift and ripple as they interact with neighbouring cavities. Some of those adjacent bubbles created by other clusters of supernovae have expanded enough to touch ours. Where they meet, the boundary grows thinner, and sometimes tunnels open between them. Astronomers have found that the local bubble connects to at least two others. The Loop 1 bubble, centered near the Scorpius-Centaurus region, and the so-called North Polar Spur, a vast arc of emission stretching above the galactic plane. These interconnections form a network of low-density corridors through which gas can flow, equalizing pressure and mixing material across hundreds of light years. The calm we feel inside the bubble is part of that larger galactic balance, a slow breathing of matter and energy between regions. The calm also gave the surrounding gas time to cool and condense. As the shockwaves dissipated and the edges of the bubble settled, the compressed shells became fertile ground for new star formation. Clouds like those in Taurus, Ophiuchus, and Lupus formed along the rim, their material gathered by the same forces that once cleared the space inside. Today, those regions are among the closest active nurseries to Earth. When astronomers point their telescopes there, they see young stars only a few million years old, surrounded by disks of dust where planets are just beginning to form. In a sense, the quiet after the storm is still creating light. It's simply doing it slowly, in the stillness left behind. On Earth, we tend to associate quiet with fragility, as if silence could be broken at any moment. But in cosmic terms, quiet can be enduring. The local bubble's tranquility has lasted far longer than the span of human civilization, and will continue for millions of years to come. It's not fragile but resilient, maintained by the delicate balance of pressures and temperatures that define it. Even the background radiation that fills it changes only gradually, fading bit by bit as the plasma cools. Every time a telescope detects that soft X-ray glow, it's reading the temperature of the aftermath, still warm, still active, but stable enough to persist. Within this calm, the Sun and its planets move slowly, following their galactic orbit as if nothing had ever happened here. The Earth turns, life evolves, civilizations rise and fall, all within a bubble that is itself the product of distant, long-faded catastrophes. It's a perspective that can be both humbling and oddly reassuring. The disasters that forged this space are ancient, their energy dispersed. What they left is a haven of sorts, a region where calm rules and the rhythm of stellar death and rebirth pauses briefly. The galaxy's larger cycles continue elsewhere, but here, for now, is peace. If you could observe this region from far above the Milky Way, you'd see the local bubble as a transparent void surrounded by a faintly glowing shell. The stars at its boundary would outline its shape, irregular, slightly flattened, and threaded with filaments. From that vantage, you might see how it fits into the galaxy's larger patchwork of cavities and clouds. Some of those neighbouring voids are older, already collapsing back into denser gas. Others are young and still expanding. Together, they form a network that gives the galaxy its cellular appearance, like bubbles in a vast cosmic foam. Our bubble, now quiet, is one cell among many, a snapshot of one phase in an ongoing pattern. The silence inside the bubble is not emptiness, but balance. Every particle of gas, every magnetic line, every faint photon plays its part in maintaining that equilibrium. The pressures inside and outside remain matched to within tiny margins. Occasionally a new disturbance, a distant supernova or a passing star, may send ripples through the region, but those ripples dampen quickly. The energy of the ancient storm is spent, and what remains is stability measured in light years and millennia, and in that stability life has had time to flourish. The sun's steady output, the Earth's stable orbit, and the relatively low flux of harmful radiation have all contributed to an environment where complexity could grow. It's not that the local bubble caused life, but that it provided a quiet stage on which life's story could unfold. The same cosmic calm that allows astronomers to see deep into the galaxy also allows us, quite literally, to exist without interruption. The bubble is both a window and a shelter. Sometimes, when scientists discuss these vast scales, it's easy to forget that they're not just abstract distances. The calm we're describing is all around you right now. Every particle of air you breathe is part of a chain of matter that once felt the shock of those long-ago explosions. Every beam of starlight you see passes through the same low-density plasma that fills the bubble. The quiet isn't somewhere far away. It's here, everywhere, woven into the fabric of our cosmic neighborhood. The local bubble will not remain as it is forever. Given enough time, the gas inside will continue to cool, and the pressure difference between the interior and exterior will fade. The walls will begin to relax inward. Eventually, perhaps tens of millions of years from now, the bubble will collapse completely, mixing back into the interstellar medium. The stars forming along its rim will move on, carrying with them the elements forged in this and earlier generations of supernovae. By then, our sun will be far away, having drifted into another region of the galaxy with its own structures and histories. The quiet we experience now is temporary, like a long pause between verses in a song that never ends. Still, for the moment, we are living in that pause. The air of space around us is calm, the energy balanced, the storms long past. The galaxies beyond may swirl and burn, new stars may flare and die. But here, inside this gently fading cavity, there is room for stillness. The universe has a way of alternating between chaos and order, noise and quiet. The local bubble is one of those rare interludes of peace, the cosmic quiet after the storm. When astronomers first turned their instruments toward the space around us, they didn't expect to find a cavity. They were looking for patterns, how starlight dims as it crosses the galaxy, how X-rays leak through the background, how dust absorbs energy and re-radiates it. The data, at first, seemed inconsistent. Stars close to the sun were shining too brightly, too clearly. Their light wasn't being scattered or reddened the way it should if the space between them and us were filled with typical interstellar dust. Something was missing, some invisible component that normally softens and dims a star's glow. The region surrounding the solar system, it turned out, was unusually transparent. The light was moving almost unfiltered, and that clarity was the first clue. When light travels through space, every particle it encounters leaves a mark. Dust grains absorb shorter wavelengths, scattering blue light more than red. Gas atoms and molecules imprint fine absorption lines on the spectrum, like fingerprints identifying their presence. By comparing the spectra of stars at different distances, astronomers can measure how much material lies between. In most directions, the amount of absorption increases steadily with distance, but toward nearby stars, the change was negligible. That meant that for tens or even hundreds of light years around us, there was almost no dust, almost no gas dense enough to interfere. Light from those stars reached Earth nearly untouched, suggesting that we occupy an unusually empty patch of the galaxy. This wasn't immediately recognised as a bubble. For decades, astronomers had only fragments of data, isolated measurements that hinted at something strange but didn't show the full picture. It wasn't until the 1970s, when instruments capable of detecting X-rays and ultraviolet radiation began mapping the sky, that the pattern started to emerge. The X-ray detectors, launched on early satellites, found a diffuse glow covering the entire sky, even in directions away from known X-ray sources. It wasn't concentrated in any one place, it was everywhere. The spectrum of that glow indicated temperatures of 1,000,000 degrees, far hotter than any ordinary interstellar cloud. The only plausible explanation was that the solar system was surrounded by hot, tenuous plasma filling a cavity, something that could emit soft X-rays but contained so little mass that it remained invisible in ordinary light. At first, there was debate. Some scientists thought the X-ray background might be generated by the solar wind interacting with neutral gas near Earth, producing local emission that only appeared to come from deep space. Others suggested it came from distant galaxies or the halo of the Milky Way. But as more precise measurements came in, especially from satellites orbiting far outside Earth's atmosphere, it became clear that a significant portion of the glow truly originated within a few hundred light years. The concept of the local bubble took shape from those observations, a region of hot, low-density gas emitting X-rays that we could detect from within. Mapping its boundaries required combining data from multiple sources. Optical and ultraviolet spectra provided distances to the nearest absorbing clouds, while X-ray maps revealed where the hot gas extended. By overlaying these datasets, astronomers began to see the outline of an irregular cavity centered roughly on the Sun's current position. It wasn't spherical. It had protrusions and gaps, extensions where the cavity merged with others, and constrictions where dense clouds pressed inward. The edges corresponded to regions of stronger absorption and to the locations of nearby star-forming complexes like Taurus and Ophiuchus. The light from those regions often showed sharp jumps in extinction, marking where the empty space of the bubble ended and denser material began. As technology improved, astronomers developed more refined ways to trace the boundary. One key method involved measuring the polarization of starlight. Dust grains align with the galaxy's magnetic field, and as light passes through them, it becomes slightly polarized. Its waves oscillate preferentially in one direction. The degree of polarization increases with the amount of dust along the line of sight. By measuring polarization for many nearby stars, scientists could infer how the magnetic field bends around the bubble's walls. The results showed a distinct pattern, field lines sweeping along the surface of an irregular cavity surrounding the Sun, further confirming the bubble's existence. Another breakthrough came from mapping interstellar sodium and calcium absorption lines. These lines are sensitive indicators of cool and warm gas, respectively. When astronomers plotted the strength of these lines as a function of distance, they saw a sharp increase beyond about 100 to 200 light-years in most directions. Inside that radius, the gas was sparse. Beyond it, it thickened dramatically. The Sun was clearly inside a large void, and its boundary was well defined by a shell of dense material. Later, the European Space Agency's Gaia mission revolutionized our understanding of this structure. By measuring the distances to over 1 billion stars with unprecedented precision, Gaia provided a three-dimensional framework for mapping the interstellar medium. Astronomers combined Gaia data with measurements of starlight reddening and dust emission from other observatories to reconstruct the local bubble in 3D. The resulting models revealed a lumpy, elongated cavity about 1,000 light-years across, surrounded by dense clouds that host nearly all of the nearby star-forming regions. It was the most detailed view ever obtained of our galactic neighbourhood, and it confirmed what decades of indirect evidence had suggested. We are indeed living inside a giant glowing shell of hot gas. The edges of the bubble, though faint, are active. Where the hot interior meets the cold molecular clouds outside, there is a thin interface region where temperatures change rapidly, and energy is exchanged. In those layers, ultraviolet radiation from nearby stars and the residual heat of the bubble ionize atoms, producing faint emission lines detectable with sensitive instruments. Observations of these boundary regions have shown that they are sites of ongoing chemistry, where molecules are broken apart and reformed, where dust grains accumulate coatings of ice and carbon compounds. The edges, in other words, are alive with slow processes of transformation. From a human perspective, the distances involved are staggering. The nearest edge of the bubble lies about 200 light-years away in some directions, 500 or more in others. Even travelling at the speed of the fastest spacecraft ever built, it would take millions of years to reach. Yet light from those edges arrives here every second, carrying information about the temperature, composition and motion of the gas. Every photon that reaches a telescope is a messenger from the boundary, telling us how the galaxy's structure changes with distance. The data reveal that the bubble isn't empty but filled with plasma at densities of about 0.005 particles per cubic centimetre, 10,000 times thinner than the air inside the best laboratory vacuum. The temperature, however, compensates for that thinness. The kinetic energy of the few particles present is enormous, and their collisions produce the faint X-rays that first gave away their presence. Because the gas is so rarefied, it cools only slowly, radiating its heat over tens of millions of years. That's why the local bubble persists. The energy from the original supernovae has dissipated but not vanished. It lingers as a diffuse glow, visible only to instruments sensitive enough to detect it. Astronomers sometimes describe this glow as a background, but it isn't uniform. There are variations in intensity and colour depending on direction. Some of those variations correspond to holes in the bubble's walls, where the cavity connects to neighbouring regions. In those directions, the X-ray emission extends farther, and we can see deeper into the galactic interior. Other directions show sharper drops in intensity, marking where the shell is thick and cold. These patterns help refine the bubble's three-dimensional map. When combined with radio observations of neutral hydrogen and far-infrared data from dust, they form a consistent picture, a lumpy, interconnected structure shaped by ancient explosions and still glowing faintly with their afterheat. The same edges that emit X-rays and ultraviolet light also reflect visible starlight. Dust grains along the bubble's boundary scatter light from nearby stars, producing a faint optical phenomenon called diffuse galactic light. Under extremely dark skies, this glow contributes to the soft background brightness of the Milky Way, though it's far too faint for the eye to distinguish. It's one more subtle reminder that we're surrounded by a vast but delicate shell, invisible in daylight, yet constantly interacting with the light that fills space. When researchers overlay maps of the bubble's edges with the positions of nearby star-forming regions, the alignment is almost exact. The Taurus molecular cloud, for example, sits right along one section of the shell. The Perseus and Ophiuchus regions trace others. This pattern supports the idea that the bubble's expansion compressed gas at its boundary, triggering new rounds of star formation. In this way, the light we see from young stars today is part of the same process that created the local bubble millions of years ago. The edge glows not just from the remnants of old energy, but from the birth of new suns. If you could travel there and look back toward the centre, the sun would appear as an ordinary star suspended in an immense, nearly empty void. Around you, the walls of the bubble would be faintly luminous in X-rays, invisible to your eyes but detectable by your instruments. In visible light, you might see filaments of gas and scattered dust reflecting the glow of nearby stars, like faint smoke illuminated from within. The scene would be still, quiet, and unimaginably vast. A horizon of diffuse colour surrounding an emptiness too perfect to describe. The light from the edge of the local bubble carries more than scientific information. It's the residue of history. Every photon began as energy from a process that once reshaped this region. The shockwaves of dying stars, the cooling of plasma, the ignition of new clouds. As that light travels inward, it passes through the vacuum where our solar system drifts, through the thin solar wind, through Earth's atmosphere, and finally into the detectors we build to study it. In a sense, when we measure those signals, we are reading the quiet biography of our cosmic neighbourhood, one wavelength at a time. Over the decades, the instruments have grown more sensitive. Space-based observatories now map the X-ray sky with precision that early astronomers could only imagine. Data from missions like Rosat, XMM Newton and Erosita have revealed finer details of the local bubble structure, confirming that it isn't isolated but part of a network of cavities shaped by multiple generations of supernovae. Each new map adds depth to the picture, showing how light from the edges merges with that of adjacent bubbles. The result is a portrait of the galaxy as a living system, full of luminous boundaries and transparent interiors, forever changing yet always recognizable. And all of it began with the simple observation that nearby stars shone too clearly, their light unsoftened by dust. That clarity, unnoticed for centuries, turned out to be a window into the very structure of the galaxy around us. The local bubble's edge, glowing faintly in invisible light, is the silent witness to the ancient explosions that cleared this space. Every photon we catch from it tells a fragment of that story, a record of energy, expansion, and quiet that defines the place we call home. If you could trace the path of the sun through the galaxy, you would see that it has never stood still. From the moment it formed, about 4.6 billion years ago, it has been moving, swept along by the rotation of the Milky Way, nudged by the gravity of passing stars, guided by the slow undulations of the galactic disk. The Sun and its planets orbit the centre of the Milky Way roughly once every 230 million years, travelling at more than 200 kilometers per second. In human terms, that motion is imperceptible, but over the lifetime of the solar system it adds up. The Sun has made nearly 20 full circuits of the galaxy since it was born. During that time, it has drifted through spiral arms, crossed regions thick with gas, and passed through spaces as clear as glass. It has never been rooted in one place. The Milky Way is not a rigid structure. Its disk is a mixture of stars and gas orbiting in slightly different directions and speeds, their combined gravity creating the patterns we see as spiral arms. The Sun moves within this disk, bobbing slightly above and below its plane in a gentle oscillation that repeats every few tens of millions of years. Like a boat on long ocean swells, it rides the waves of the galactic gravitational field, spending part of its time above the midplane and part below. This motion, combined with its orbit around the centre, means that the solar system is constantly sampling new regions of interstellar space. Every few million years, the environment changes, the density of gas, the strength of the magnetic field, the background radiation, all subtly shifting as we move. When the Sun was young, it likely formed within a dense molecular cloud, a cold nursery where stars are born in clusters. For a time, it shared space with dozens or perhaps hundreds of siblings, other stars born from the same cloud. Over the first 100 million years, gravitational interactions and the motions of the cluster members dispersed them, sending each star on its own path around the galaxy. Those siblings are still out there somewhere, scattered through the spiral arms, faintly recognizable by their matching chemical fingerprints. The Sun left its birth cloud long ago, and has since travelled through a variety of environments. The space it occupies now, the interior of the local bubble, is only its most recent home, one stop in a long galactic journey. Reconstructing that journey is challenging, but not impossible. With modern data from the Gaia mission, astronomers can measure the Sun's motion with extraordinary precision and trace nearby stars backward in time to see where their paths intersected. Using this method, they can estimate when the solar system entered the local bubble, probably within the last 5 to 10 million years. Before that, the Sun was likely moving through denser clouds of the interstellar medium, regions more typical of the galaxy's background density, As it entered the bubble, the surrounding gas density dropped by an order of magnitude, and the boundaries of the heliosphere expanded outward. The change wasn't sudden. It would have unfolded over tens or hundreds of thousands of years, imperceptible to any observer on Earth. But in cosmic terms, it was a transition into a new environment, a quieter and more open stretch of the galactic landscape. The idea that the Sun is drifting through such varied terrain is not new. Astronomers have long known that stars move relative to one another, and that the local interstellar environment can change dramatically over time. Each star creates its own bubble in the interstellar medium, blown by stellar winds and magnetic fields. When one of these bubbles encounters another, they merge, overlap, or distort. The local bubble itself is part of a network of such cavities. The Sun's motion carries it from one to another, like a ship passing through a chain of vast invisible harbours. The heliosphere, the Sun's personal bubble of influence, acts as both probe and shield, adjusting its size and shape depending on the pressure of the surrounding interstellar gas. In denser regions, it contracts. In thinner regions, it expands. Inside the local bubble, it enjoys more room to breathe. Evidence for this wandering path can be found not only in stellar data, but also in isotopic traces left on Earth. The discovery of iron-60 in deep ocean crusts and lunar samples suggests that one or more supernovae exploded near the solar system within the past few million years. These events likely occurred at the edges of the local bubble as it expanded, and the Sun may have been close enough to catch some of the radioactive debris. That debris settled on Earth and the Moon, marking a timestamp in the geological record. It tells us that the Sun was already inside or near the boundary of the bubble when those explosions happened. The galaxy leaves fingerprints, and they remain for us to read millions of years later. The Sun's current trajectory carries it roughly toward the star Vega in the constellation Lyra, though the direction changes slowly as we orbit the galactic centre. In about 20 million years, it will have crossed the local bubble entirely and moved into a different region of the interstellar medium, perhaps one of the adjacent cavities that connect to ours through narrow tunnels. These transitions are so slow that even on geological timescales, they pass almost unnoticed, but they shape the environment through which the solar system moves. The density, temperature, and composition of the interstellar gas all influence how the heliosphere behaves, which in turn affects the flow of cosmic rays and interstellar dust that reach the inner planets. In denser regions, the heliosphere would shrink, compressing the space protected by the solar wind. More cosmic rays would reach Earth, potentially affecting the upper atmosphere, and even the rate of cloud formation. Some researchers have suggested that variations in the interstellar environment might have played a role in long-term climate patterns over the history of the planet, though the evidence remains tentative. In any case, the solar system's motion through the galaxy is not just a change of scenery, it's a slow modulation of the cosmic conditions that envelop us. The local bubble represents a relatively benign phase in that journey, a period of reduced density and calm. To visualize the Sun's path, imagine drawing a line through the galaxy's disk, a long looping curve winding through bright and dark regions, through spiral arms and gaps. The line crosses clouds of gas, passes through bubbles like ours, and weaves around clusters of stars. Each segment of the journey corresponds to millions of years of time, enough for continents on Earth to shift and species to evolve. The galaxy's structure in turn shifts around us. The spiral arms themselves are not fixed, they're density waves, regions where material temporarily crowds together. The Sun drifts into and out of these arms every 100 million years or so, each passage bringing encounters with new molecular clouds and star-forming regions. Between the arms, it travels through quieter inter-arm spaces like the one it occupies now. The local bubble sits near the boundary between two of those larger arms, the Sagittarius Carina and the Perseus arms. It's a kind of interarm refuge, a gap between the denser lanes of star formation. That positioning helps explain its relative emptiness. The cluster of supernovae that carved it out occurred in an area already less crowded with material, allowing their shockwaves to expand freely. The Sun's arrival in this region was another accident of galactic motion, one among countless coincidences that define its journey. There is no fixed destination. The orbit is a loop without an endpoint, a continuous migration through environments that change only over spans of time too long for any life to notice. Despite that vastness, we can trace the Sun's motion in surprising detail. Gaia's measurements of stellar positions and velocities allow astronomers to build three-dimensional models of the local neighbourhood, showing how nearby stars move relative to one another. By integrating these motions backward, they can simulate where the Sun and its neighbours were millions of years ago. The results place the Sun near the centre of the local bubble today, having entered from a direction roughly aligned with the Scorpius-Centaurus association, the same cluster whose supernova created the bubble in the first place. In effect, the Sun drifted into the clearing left behind by those explosions, taking up residence in their wake. This realization gives our current environment a kind of narrative. The Sun wasn't here when the bubble formed. It came later, wandering into a space already carved and calmed by earlier generations of stars. It's as if our solar system moved into the ruins of an ancient city, its walls long cooled, its fires extinguished, but its shape still defining the landscape. The remnants of those long-dead stars now form the boundaries of our cosmic neighbourhood. Their ashes float invisibly in the thin gas around us, and their energy still defines the pressure and temperature of the medium we inhabit. The Sun, in passing through, became part of that history, just as future stars will one day pass through the remains of what we leave behind. The wandering path also means that the sky we see, the arrangement of stars, the density of the Milky Way's band, even the background glow, changes slowly as we move. Millions of years from now, the constellations will be unrecognizable. The familiar patterns of Orion, Scorpius, and Lyra will have dispersed as their stars move along their own trajectories. The Sun's surroundings will be filled with new neighbours, stars we can't yet see. The entire character of the night sky is transient, shaped by the same slow drift that brought us here. The local bubble is just one frame in a long movie, a snapshot of the galaxy's evolving structure. For now, that snapshot is unusually clear. The transparency of our surroundings allows us to see deep into the Milky Way, to study the far edges of our own spiral arm and even glimpse others beyond. That clarity is a gift of location, a consequence of being inside a cavity of thin gas. From denser regions, the view would be obscured by dust. In that sense, the Sun's wandering path has brought us not just to safety, but to a vantage point. It's as though, after crossing crowded regions filled with fog, we've emerged into open air, where the view stretches for thousands of light years. When you look up at the night sky and see the Milky Way arching overhead, what you're really seeing is the galaxy from within one of its own gaps. The stars you see most clearly are those shining through the local bubble's transparent interior. Their light reaches you with minimal distortion, a straight beam across the cavity. That light carries the memory of the Sun's path, the environments it has passed through, the structures it has entered, the clarity it now enjoys. It's a reminder that our position in space is never fixed, but always part of a larger motion. The Sun's journey through the local bubble is still underway. In another few million years, it will begin to approach the far wall, perhaps passing into a neighbouring cavity, perhaps grazing a denser cloud. Whatever happens, the change will be gradual. The heliosphere will adjust, the flow of cosmic rays will shift, and the conditions of interstellar space around us will evolve. Life on Earth, if it still exists, will adapt without noticing. The galaxy moves at a pace that dwarfs every measure of human time. All the while, the Sun will continue its orbit, one of billions of stars following their own wandering paths. Some will cross dense clouds and trigger new bursts of star formation. Others will pass through voids like ours, Together their motions create the slow dance of the Milky Way, a pattern of stars and gas forever rearranging, forever renewed. And in that endless motion, the sun's current stop inside the local bubble is a moment of calm, a pause in a journey that has no destination. The stars that once exploded here are gone, their debris forming the walls around us. The stars that will one day form from those walls have not yet ignited. Between them we drift, carried by the galaxy's rotation through a space shaped by ancient fire and cooled into peace. If we could step outside the local bubble and look back, we would see that our home region is not an isolated pocket, but part of a tangled system of connected cavities, clouds, and filaments. The galaxy's interstellar medium is far from uniform, and the space just beyond the bubble's boundaries is alive with structure. These are our neighbours in the void, massive molecular clouds, young star clusters, and long filaments of dust that define the edge of our cosmic neighbourhood. From the inside, the bubble feels empty and clear, but beyond its perimeter the galaxy thickens again, and the quiet gives way to the gentle hum of creation. In nearly every direction, the walls of the local bubble press against denser regions of gas. Some are so thick and cold that they block visible light, appearing as dark patches against the starry background. Others glow faintly in the infrared, warmed by starlight or newly formed stars. These neighbouring clouds are among the closest and best studied in the galaxy because they are near enough for us to observe in detail. When astronomers map them, they find that they trace the irregular shape of the bubble's outer shell. The pattern is unmistakable. The cavity carved by ancient supernovae forms the heart of our local region, and along its edge, gas and dust compressed by those explosions have given rise to new generations of stars. To the north and east of the solar system lies the Taurus molecular cloud, a sprawling complex of cold gas about 430 light-years away. It stretches across dozens of light-years, its filaments rich with carbon monoxide and dust. This region is one of the nearest active star-forming sites, home to hundreds of young stars less than a few million years old. Many of them are surrounded by disks of gas and dust that may one day form planets. When astronomers point infrared telescopes towards Taurus, they see these disks glowing softly, the heat from newborn stars warming the material around them. The entire region forms part of the local bubble's boundary, where the outward-moving shell from ancient supernovae pressed into surrounding gas and set off gravitational collapse. To the south lies Ophiuchus, another dense cloud complex located roughly the same distance away. Like Taurus, it marks the bubble's edge, and within it stars are still forming. The Ophiuchus cloud is smaller but more compact, its dense core shrouded in dust that hides the young protostars inside. Observations in infrared and radio wavelengths reveal jets of gas streaming from those protostars, evidence of ongoing accretion. The light from these newborn suns never reaches Earth directly in visible form. It's absorbed and re-emitted by the dust. But in infrared, the region glows brightly. The energy driving that glow comes indirectly from the same processes that carved out the local bubble. The compressed shell that became Ophiuchus owes its shape to the overlapping shockwaves that swept through this part of the galaxy millions of years ago. Farther away, in the constellation Perseus, lies another key neighbour, the Perseus molecular cloud, a vast and active region about 1,000 light-years from us. This cloud too forms part of the broader network of cavities and shells surrounding the local bubble. In 2022, astronomers using Gaia and radio data traced the full three-dimensional structure of these regions and found that Perseus and Taurus sit on opposite sides of a vast hollow cavity connected to our own. The entire arrangement looks like a chain of bubbles fused together, each one the remnant of past supernovae. The local bubble is simply the nearest and best mapped of them. In addition to these dense clouds, the local bubble borders several diffuse regions where the gas is warmer and thinner. The so-called local fluff is one of them, a small warm cloud of partially ionized gas that currently envelops the solar system inside the bubble. It's only a few dozen light-years across, with a density of about 0.3 atoms per cubic centimetre, denser than the bubble's average interior but still tenuous compared to Earth's atmosphere. The Sun has been moving through this cloud for perhaps the last 100,000 years, and it slightly affects the shape of the heliosphere by increasing the external pressure on one side. Once the Sun moves beyond it, the conditions of interstellar space around us will shift again. The local fluff is not unique. It's part of a complex of small clouds scattered through the interior of the bubble, fragments left over from its formation. When astronomers create three-dimensional maps of these structures using data from Gaia, they find a surprising degree of organization. The nearby clouds, Taurus, Ophiuchus, Lupus, Chameleon, and others, form an almost continuous ring around the Sun, outlining the bubble's perimeter. This ring coincides with regions of active star formation, where the density of gas is high enough for gravity to take over. The implication is that the bubble's expansion triggered this star formation, compressing the gas along its boundaries just as a sound wave compresses air. Each of these clouds is now evolving independently, forming clusters of young stars that will, in time, disperse and move away, leaving behind new cavities of their own. The relationship between the bubble and its neighbours is dynamic. The edges where hot and cold gas meet are zones of constant exchange. The hot plasma inside the cavity leaks energy into the cooler molecular gas, while radiation from young stars at the boundary heats and ionizes the surrounding material. Magnetic fields thread through both regions, channeling gas flows and shaping the filaments we observe. These interactions happen on timescales of millions of years, but they are crucial for maintaining the balance of the interstellar medium. Without them, the galaxy's structure would quickly become either too smooth or too chaotic. The boundaries between cavities like ours and dense clouds like Taurus are the galaxy's interface zones, where destruction and creation meet. In some directions, the local bubble opens directly into other cavities. The Lupi bubble, for example, lies adjacent to ours, formed by a separate cluster of supernovae in the Scorpius-Centaurus association. The two cavities are connected by a narrow tunnel of low-density gas, through which hot plasma and radiation can flow. Astronomers refer to this combined structure as a superbubble complex, a larger feature created when multiple generations of stellar explosions overlap. The local bubble is just one cell in this network, surrounded by others that merge and interact. These interconnections explain why the X-ray emission from the region is not perfectly uniform. Some directions show stronger glow where the bubbles meet, while others are dimmer where the shell is thicker. To the west of the solar system lies the Orion-Eridanus superbubble, another vast structure associated with the Orion star-forming region. It's farther away, but its boundary touches or nearly touches ours in some models. The Orion complex, with its bright nebulae and young massive stars, is an example of what our region might have looked like before the ancient supernova faded. Its glowing arcs of ionized gas are the visible counterparts of the invisible shell surrounding us. Where Orion's energy pushes outward, it shapes the interstellar medium in the same way the Scorpius-Centaurus explosions once did here. The galaxy is full of these repeating patterns, bubbles forming, merging, collapsing, and reforming, each at a different stage of the cycle. Even the dark clouds near the bubble's edge are not static. The Taurus filaments, for example, are threaded with magnetic fields that guide the motion of gas. Observations with radio telescopes show that these filaments are slowly flowing toward regions of higher density, where they may eventually collapse to form new stars. The timescales are long, millions of years, but the process is ongoing. In Ophiuchus, new protostars are already forming in the densest parts, their radiation and winds beginning to erode the surrounding material. These local processes will eventually reshape the bubble's boundary, creating small openings or extending it into new directions. For astronomers, the proximity of these clouds is a gift. Because they are so close, they can be observed in detail at multiple wavelengths, from radio to X-rays. Instruments like the Atacama Large Millimeter Array and the Herschel Space Observatory have mapped the cold dust and molecules within them, revealing intricate filamentary structures. Data from Gaia adds the third dimension, showing how these filaments curve and twist through space. When the maps are combined, they reveal a nearly continuous shell of dense gas surrounding the local bubble. A confirmation that the cavity is not just a theoretical construct, but a tangible feature of our galactic neighbourhood. From our vantage point inside the bubble, these clouds define the limits of what we can see in different wavelengths. In visible light, they block our view, casting dark shadows against the star field. In infrared, they glow gently, warmed by distant starlight. In radio, they emit at specific frequencies that trace their composition. Every observation adds another layer of detail to the picture, and together they tell a consistent story. The local bubble is a hollow region carved out of the interstellar medium, surrounded by a chain of dense clouds, where the next generation of stars is being born. The idea that we are surrounded by star-forming regions has a certain symmetry. The same supernovae that cleared out this space also created the conditions for new stars to form around it. The violence that once swept this region clean has given rise to the calm we inhabit, and to the light we see from the edges. Each of the neighbouring clouds represents a different phase in that continuing story. Some are just beginning to form stars, others are well along in the process. All are connected by the history of the local bubble, their positions marking the remnants of the same chain of events that began millions of years ago. From within our quiet void, it's easy to forget that just beyond its boundaries lies such activity. The sun's light travels through the bubble almost unimpeded, reaching the walls with little scattering. There it meets dense gas and dust, which absorb and re-radiate it in different wavelengths. The night sky we see from Earth contains traces of those interactions. The diffuse glow of dust, the faint arcs of emission nebulae, the dark lanes where light cannot pass. Those patterns are the visible outline of our cosmic neighbourhood, drawn in the language of light and shadow. If we could move outward toward one of those clouds, the change would be gradual. The interstellar gas would grow denser, the magnetic field stronger, and the radiation from young stars more intense. Dust would begin to block more starlight, and the sky would take on a different character, dimmer, more diffuse. The transition from the empty interior of the bubble to the crowded edges would not be abrupt but smooth, a gradient between transparency and opacity. Somewhere in that gradient lies the boundary that defines the local bubble. It is not a wall in the ordinary sense, but a zone where the galaxy's contrasting conditions meet and blend. These neighbours in the void are the bridge between past and future. They hold the materials that will one day form new stars and planets, perhaps new civilizations that will look back on this same region from their own vantage points. The gas that makes up Taurus or Ophiuchus today will, over millions of years, condense, ignite, and shine. Some of those future stars may even illuminate the remnants of the local bubble's walls, turning our quiet void into a backdrop for new light. The galaxy renews itself continuously, and we happen to live in a moment of calm between its great breaths. Surrounded by these vast structures, our position feels both remote and connected. The emptiness around us is not isolation but balance, maintained by the presence of dense, creative regions just beyond. The neighbours of our bubble are reminders that the universe never truly rests. Even in apparent stillness, it's preparing the next act. The local bubble, with all its silence and clarity, is encircled by the engines of future stars, their raw material waiting quietly in the dark. And as we drift through this hollow space, the light from those edges continues to reach us, whispering the story of how calm and chaos coexist in the same vast galactic landscape. If we could step far enough away from the Milky Way to see it all at once, we would notice that its light doesn't spread evenly, but pools into patterns, spiral arms of stars, clouds of dust, and wide, dark lanes that twist between them. Somewhere in one of those arms, halfway between the galaxy's centre and its edge, a thin disk of light holds our sun. And if we could zoom in closer and closer, Peeling back the layers of starlight and gas, we would find that the space immediately around the Sun is hollow. It is shaped not by chance but by history. A cavity, an irregular bubble carved into the galaxy's thin gaseous skin. This hollow, the local bubble, defines the shape of our galactic home. It is not a perfect sphere. It is a long, warped tunnel stretching roughly 1,000 light-years across, expanding in some directions, squeezed in others, and connected to neighbouring cavities through narrow corridors of thinner gas. In maps, the bubble looks a bit like a distorted peanut or a lopsided hourglass, its two wider lobes joined by a constricted waist. But such comparisons are only approximations. In truth, the local bubble has no neat geometry. Its walls are rippled and ragged, marked by patches where the gas is thicker or thinner, where the compression from ancient supernova shockwaves was stronger or weaker. In some places, the boundary is sharp, a sudden jump from low-density plasma to cold molecular gas. In others, it is diffuse, blending gradually into the surrounding medium. The structure is dynamic, constantly shaped and reshaped by pressure differences, magnetic fields, and the movement of nearby stars. Astronomers have worked for decades to chart this complex form. Early attempts relied on rough estimates of how starlight dims with distance, giving only two-dimensional hints of the boundary. Later, with better parallax data and large catalogues of stellar spectra, they could construct three-dimensional models. The Gaia mission finally provided the level of precision needed to map the bubble in detail. By combining Gaia's distances with measurements of how much dust and gas obscure each star, researchers have produced volumetric reconstructions of the local interstellar medium. These maps reveal the local bubble's full extent, a cavity roughly 1,000 light-years long, 600 light-years wide, and perhaps 400 light-years tall, centered near the Sun but tilted relative to the galactic plane. The bubble's walls form a chain of dense molecular clouds, including Taurus, Perseus, Ophiuchus, Lupus, and Chameleon. Each of these clouds marks part of the shell where gas was compressed by overlapping shockwaves from supernova millions of years ago. Together, they create a kind of irregular boundary around the void, though the shell is incomplete. In several directions, particularly toward the Scorpius-Centaurus association, the boundary opens into adjacent cavities such as the loop and superbubble. These openings allow the hot gas inside to flow outward, balancing pressure across regions. The overall shape resembles a piece of Swiss cheese, full of holes, interconnected tunnels, and overlapping voids. If we could see the local bubble in light our eyes could detect, the sky would look unfamiliar. The edges would appear as faint, hazy arcs outlining enormous distant clouds. The space between would seem unnaturally clear, a vast transparency surrounding the Sun. In truth, most of the bubble's structure emits in wavelengths invisible to us. X-ray and ultraviolet radiation mark the hot plasma inside, while infrared light traces the dust along the walls. When astronomers combine observations from these different wavelengths, the result is a layered view of the bubble's anatomy. A glowing interior, a thin interface of warm gas, and an outer shell of cold molecular material. The maps derived from these data reveal not just the bubble's shape, but its orientation. Its long axis tilts about 20 degrees relative to the galactic plane, suggesting that the forces that carved it were uneven, perhaps stronger explosions or denser material on one side. The Sun lies slightly off-center, not exactly in the middle but closer to one end, where the boundary is thinner and more irregular. In some directions, the shell is only 200 light-years away. In others, it stretches more than 500. The asymmetry hints at the sequence of supernovae that created it. Explosions occurring in slightly different locations and times, overlapping to form an irregular composite cavity rather than a single, uniform sphere. When astronomers render these structures in 3 dimensions, the view is mesmerizing. The bubble appears as a glowing cavity surrounded by clouds arranged in a ring-like formation. Many of the nearest star-forming regions sit precisely on that ring, confirming that the shockwaves from the original supernovae compress the gas at the edges, igniting new generations of stars. The positions of these young clusters, Taurus, Perseus and others, trace the contour of the shell like beads on a thread. Their alignment is too consistent to be coincidence. It shows that the local bubble isn't just an empty space, but an engine of creation, its walls still active after millions of years. Beyond the local bubble, similar structures fill the galaxy. Each one is the aftermath of clustered supernova, and together they form a sponge-like network of cavities and filaments extending across the Milky Way's disk. The galaxy's interstellar medium is not a uniform gas, but a labyrinth of connected voids. In some regions, the bubbles merge to create vast superbubbles spanning thousands of light years. In others, they overlap only slightly, forming narrow channels. The local bubble is one cell in this grand structure, linked to its neighbours by tunnels of hot gas. The boundaries of these cells define where new stars can form, as compressed shells cool and fragment under gravity. This network gives the galaxy a texture, an intricate three-dimensional pattern of density and light. When we observe the Milky Way in X-rays, we see bright arcs and loops corresponding to the hottest gas in these cavities. In radio wavelengths, we see long filaments tracing magnetic fields along their edges. In optical light, the densest parts appear as dark clouds silhouetted against the stars. All of these features are aspects of the same underlying structure, a galaxy sculpted by cycles of stellar birth and death. The local bubble is one of the smallest and most detailed examples of this process, a laboratory for understanding how energy shapes the interstellar medium. Our position inside the bubble gives us a unique perspective. Because the cavity is so clear, we can see farther into the galaxy than we could from a denser region. The absence of nearby dust means that starlight travels to us with minimal interference, allowing astronomers to study distant clusters and nebulae that would otherwise be obscured. At the same time, being inside the bubble provides an opportunity to study the physics of the interstellar medium up close. The boundary regions, with their steep temperature and density gradients, are natural laboratories for observing how energy flows between hot and cold gas. These transitions are key to understanding how the galaxy maintains its balance between expansion and collapse. In a sense, the local bubble is both a product and a participant in that balance. The energy of the ancient supernovae that formed it still defines the pressure inside, while the cooling of its edges regulates how new clouds form. The bubble's shape evolves slowly, responding to the motions of the surrounding material. As nearby stars move and new ones are born, their winds and radiation will eventually erode or reinforce parts of the shell. Over the next few million years, the structure will change. Holes will widen, new filaments will form, and perhaps the bubble will merge completely with one of its neighbours. The geometry of the local bubble also helps explain the distribution of young stars in our region. Nearly all of the nearby star-forming regions align along its surface, forming a kind of galactic belt known as the Gould Belt. This ring of young stars and clusters encircles the sky at an angle to the galactic plane, and for decades astronomers puzzled over its origin. The realization that the Gould Belt coincides with the boundary of the local bubble solved much of the mystery. The belt is essentially the visible outline of the bubble's rim, populated by the stars born from the gas compressed along it. The Sun, sitting near the centre of this configuration, has a panoramic view of its own neighbourhood's history. The structure's irregular shape has subtle effects on our observations. Because the boundary is closer in some directions than others, the amount of interstellar extinction, the dimming of starlight, varies across the sky. Regions toward the galactic centre, where the shell is denser, appear dustier and redder, while directions toward the galactic poles, where the cavity opens into larger voids, show less reddening. These variations were among the first clues that something unusual surrounded the solar system. Today, they serve as a calibration for models of interstellar dust distribution. The bubble, once a source of confusion, is now a reference point for understanding the galaxy's transparency. The The shape of our galactic home is also defined by the motion of the gas within it. The interior plasma is not static, but moves in slow convection-like flows driven by pressure differences. Magnetic fields guide these motions, stretching them into long, curved paths that trace the cavity's shape. At the boundaries, instabilities sometimes form, ripples where hot gas pushes against cold. Over time, these ripples can evolve into filaments or break into smaller clouds, seeding new structures within the shell. Even in apparent stillness, the bubble is alive with motion, its geometry a frozen snapshot of continual transformation. From Earth, we experience none of this motion directly. The scale is too vast, the changes too slow. Yet the evidence surrounds us in every direction. The pattern of bright and dark regions in the Milky Way's band, the positions of nearby molecular clouds, the faint X-ray glow of the sky, all reflect the shape of the local bubble. Our planet, orbiting its star, sits inside a vast invisible chamber, sculpted by forces long past. Its boundaries define not just where we are in space, but what kind of space we occupy. A clear, hot, low-density region, bounded by cool, dense clouds that give birth to new stars. If we could draw a simple picture of our galactic home, it would show the sun near the centre of a transparent cavity surrounded by glowing walls. Beyond those walls, clouds gather and new stars ignite. Beyond them lie other bubbles, other cavities, other waves of formation and destruction. The Milky Way, seen in this light, is a web of hollow spaces and bright edges, a galaxy made not just of stars, but of the spaces between them. The local bubble is our small part of that web, the cell in which our sun currently drifts. In time, the shape will change again. The same processes that built it will eventually tear it apart. New supernovae will carve fresh cavities. Old ones will collapse and fill with gas. The outlines we map today are only temporary, snapshots of an evolving galaxy. But for now, the local bubble defines our surroundings, a vast gentle hollow that shelters us in its centre, its walls alive with the light of young stars. The quiet that fills the local bubble today is not complete. Beneath its stillness lies a memory, an imprint of the violent forces that gave birth to this cavity millions of years ago. Though the shockwaves of the original supernova have long since faded, their echoes still linger in the form of faint radiation, drifting particles and magnetic scars woven through the interstellar medium. To study these remnants is to listen to the last reverberations of explosions that once reshaped the local galaxy, each echo carrying information about when and where the events occurred. When a massive star explodes, it does not vanish cleanly. The outward surge of gas leaves behind a pattern that takes millions of years to erase. The shockwave travels through the surrounding medium, compressing and heating it, and the expelled material, rich in heavy elements, continues to expand long after the visible flash has faded. The radiation, particularly in X-rays and gamma rays, decays slowly, while the magnetic fields created by the explosion remain tangled across vast distances. Even as the gas cools and merges into the ambient interstellar environment, the space retains subtle differences in temperature, composition, and magnetic orientation. These are the echoes of supernovae, the fingerprints of ancient energy still etched into the galaxy's fabric. In the case of the local bubble, at least 15 to 20 supernovae are thought to have occurred over a span of about 10 million years, originating mostly in the Scorpius-Centaurus-OB association. Each one added a layer of heat and pressure to the growing cavity. The collective effect was not a single blast, but a prolonged, overlapping sequence of explosions, each reinforcing the clearing created by its predecessors. Their combined power carved the 1,000-light-year-wide space we inhabit today. Even now, that history is visible in traces scattered across multiple kinds of data: cosmic rays, radioactive isotopes, and subtle shifts in the temperature and density of the interstellar gas. One of the most direct pieces of evidence for recent nearby supernovae comes from Earth itself. deep-sea sediments and lunar samples contain measurable quantities of iron-60, a radioactive isotope with a half-life of about 2.6 million years. Because it decays relatively quickly on cosmic timescales, any that existed when the Earth formed would have vanished long ago. The presence of fresh iron-60 in geological layers means it must have arrived recently, most likely carried by dust from one or more supernovae within a few hundred light-years of Earth. Analyses of those layers suggest two distinct peaks in deposition, one about 2.5 million years ago and another around 7 million years ago. These correspond closely to the expected timeline of the final explosions that contributed to the local bubble's formation. The arrival of iron-60 on Earth would not have been catastrophic. The distances involved were too great for the radiation to cause harm, but close enough for microscopic grains of supernova debris to drift through the solar system. Some of that material settled in the oceans, where it became trapped in sediments and ferromanganese crusts. It is, quite literally, a dusting of stardust from the events that sculpted our galactic home. The same isotope has been found on the Moon, and even in samples of interplanetary dust, confirming that it pervades the solar system. Each atom of it is a survivor from a nearby stellar death, a tiny messenger from the explosions that cleared this region of the galaxy. Beyond isotopes there are other echoes. Cosmic rays, high-energy particles accelerated by supernova shockwaves, still move through the local bubble. These particles, mostly protons and atomic nucleus, travel at nearly the speed of light, spiraling along magnetic field lines and scattering off irregularities in the galactic magnetic web. Some of them originate from the same cluster of supernovae that formed the bubble, still diffusing outward millions of years later. Though their density is low, they form a steady background that fills the galaxy, and their influence extends even to Earth. They contribute to ionization in the upper atmosphere, affect the chemistry of clouds, and occasionally leave tracks in detector materials deep underground. Each particle's path is a relic of the forces that launched it, tiny sparks from ancient explosions still flickering through the void. The magnetic structure of the local bubble itself may bear the imprint of those same supernovae. When the explosions occurred, their shock waves compressed and amplified the existing galactic magnetic field, stretching it along the expanding shell. Over time, as the gas cooled and the bubble stabilized, those magnetic lines remained frozen into the walls, tracing the pattern of the original expansion. Observations of polarized starlight show that magnetic fields around the Sun indeed curve along the boundaries of the cavity, following its contours. In some directions, the field strength increases slightly, marking areas where the shell is thicker or where multiple bubbles intersect. These features serve as silent records of the energy that once pulsed through the region, preserved not in motion or sound, but in invisible lines of force. The echoes also appear in light. The faint X-ray and ultraviolet glow that fills the sky originates from the million-degree plasma inside the bubble. This glow is the residual heat of the supernovae, still slowly radiating away. Its intensity varies depending on direction, stronger where the bubble opens into other cavities, and weaker where the shell is thicker. By mapping that glow, astronomers can reconstruct the bubble's shape and estimate its age. The fact that the interior remains so hot after millions of years shows how efficient the overlapping explosions were at heating the gas, and how slowly such a tenuous medium cools. Every photon of that diffuse radiation is an echo, a last whisper of fire from stars that no longer exist. The distribution of young stars along the bubble's edge adds another layer of evidence. Many of these stars belong to the Scorpius-Centaurus complex, whose subgroups, Upper Scorpius, Upper Centaurus Lupus, and Lower Centaurus Crux, represent successive generations of star formation. The ages of these groups decrease with distance from the bubble's centre, forming a timeline that matches the sequence of supernovae. The oldest subgroup contains stars about 15 million years old, roughly when the first explosions began. The youngest, only a few million years old, sits along the current boundary, born from gas compressed by the expanding shell. This gradient in stellar ages is a spatial echo, a fossilized record of how the energy from dying stars triggered the birth of new ones. Even the sun's motion through the bubble can be seen as part of that echo. The solar system's current position near the center of the cavity and its trajectory relative to nearby star clusters suggest that it entered the region only after the main sequence of explosions had ended. As it moves through the lingering heat and radiation, it traces the final stages of the bubble's evolution. The stable environment we now experience, low density, low turbulence, and reduced cosmic ray flux compared to denser regions, is itself an aftermath. We live in the echo's calmest moment, when the energy has mostly dissipated but the structure remains. Across the galaxy, similar cavities tell the same story. The Cygnus Loop, the Orion-Eridanus superbubble, and countless others each bear the signatures of their own sequences of supernovae. In some, the echoes are younger and louder, the gas still hot and bright, the shockwaves still visible as arcs of glowing hydrogen. In others, like ours, the echoes are faint, their energy dispersed but their influence enduring. Each of these structures represents a single phrase in the Milky Way's ongoing conversation between death and renewal. The connection between supernovae and the interstellar medium extends beyond structure. The elements created in those explosions seed the galaxy with the building blocks of planets and life. The iron in the Earth's core, the calcium in our bones, the oxygen we breathe, all were forged in the nuclear furnaces of massive stars and released in their deaths. The very matter that now forms our world once existed in the interiors of the same kinds of stars that created the local bubble. In that sense, the echoes of supernovae are not just physical remnants, they are chemical legacies. The debris of those long-gone suns lives on in every atom of our bodies. It is striking to think that we can detect such echoes at all. The signals are faint, buried in noise, spread thin across space and time, yet modern instruments can read them with astonishing precision, turning scattered clues into a coherent history. A grain of radioactive dust in ocean sediment, a faint glow of X-rays in the sky, a pattern of polarization in starlight. All these are pieces of the same story. When combined, they reveal a consistent timeline, a chain of explosions beginning about 15 million years ago, carving out a cavity, heating it, shaping its walls, and leaving behind a structure that still defines our environment. The local bubble, then, is more than a void. It is an archive. Every photon that escapes from its hot interior, every charged particle that drifts through it, and every magnetic line that traces its boundary carries part of the record of those long-past events. The space around the sun is not empty but filled with memory, a fossil of energy that once roared through it. We move through those memories every moment, our planet circling quietly within their remains, and as those echoes fade ever further, they continue to influence the galaxy around us. The walls they left behind have become nurseries for new stars, the compressed gas at their edges igniting to form light once again. The cycle repeats itself endlessly. Explosion, expansion, cooling, compression, birth. The Milky Way's glow is built on these rhythms, each region at a different point in the sequence. To understand our bubble's next stage, we only need to look at its edges, where those new stars are forming even now, breathing light into the remnants of the old. The echoes of supernovae are the background music of the galaxy, never gone, only softened by distance and time. They are the quiet resonance beneath the visible beauty of the stars, the lingering memory of creation through destruction. And as the local bubble cools, as its boundaries continue to glow with new light, we are living within one of those echoes, carried forward by the same energy that once tore this space apart. The walls of the local bubble are not dead structures. They are active, dynamic frontiers where the quiet plasma of the interior meets the cool, dense gas of the surrounding molecular clouds. Those walls, stretching hundreds of light years in every direction, are glowing with the slow fire of creation. When astronomers map the sky in ultraviolet, infrared, and radio light, they see that the edges of the bubble are alive, seeded with star-forming regions, pockets of energy where gravity and radiation compete. In the dark reaches of Taurus, Perseus, Ophiuchus, Chamaeleon, and Lupus, young stars are being born even now. They are the children of ancient supernovae, the luminous legacy of destruction turned to light. The local bubble breathes that light, the fading exhalation of old stars becoming the first breath of new ones. When the supernovae that carved this space out of the interstellar medium went off millions of years ago, their shockwaves didn't simply clear gas away. They pushed it outward, compressing it into dense shells. Over time, those shells cooled and fragmented, and in their thickest parts, gravity began to pull matter together. The same pressure that had created the void now created its opposite, a ring of new suns along the boundary. Today, that process continues in slow motion. The edges of the bubble are threaded with molecular clouds where hydrogen atoms have combined into H2, where dust has gathered, and where gravity is quietly at work. These clouds, cold and opaque in visible light, are bright in the infrared. Their faint, curling filaments trace the outlines of the bubble's breathing surface, marking the places where creation is underway. One of the most remarkable findings of recent years came from a 2022 study combining data from Gaia, the Planck Observatory, and radio surveys of interstellar gas. When astronomers reconstructed the three-dimensional structure of the local bubble, they found that nearly all nearby star-forming regions lie precisely along its surface, not scattered randomly, not coincidentally, but arranged in a continuous ring that outlines the cavity's boundary. This discovery confirmed a picture that scientists had suspected for decades, but never fully proven, that the local bubble is not just an empty shell but a star-making machine. Its expansion triggered waves of formation that have persisted for millions of years. The young stars along its rim, many less than 10 million years old, are the living proof. These stars are visible reminders of how energy moves through the galaxy in cycles. Each generation of massive stars burns fast and dies violently, clearing space and compressing gas to form the next. The local bubble is one phase in that rhythm, a snapshot of renewal. The Sun happens to be drifting through this stage at the moment when the cycle's destructive and creative forces are balanced. The massive stars that created the bubble are long gone, but their influence endures in the light now blooming at its edges. The process is so vast and slow that no single observer could ever see it from start to finish, but the evidence is unmistakable. The same energy that once tore this region apart is now building it again. The newly born stars along the bubble's rim emit light across the spectrum. In visible wavelengths, many of them are still hidden behind dust, but their ultraviolet radiation leaks through, illuminating nearby gas. In infrared, the dust itself glows softly, warmed by that radiation. In radio frequencies, molecules like carbon monoxide and ammonia trace the coldest, densest cores where new stars are forming. Observing these regions in different wavelengths is like listening to an orchestra of processes, each one playing at its own tempo. The low-frequency hum of molecules marks where gas is gathering. The infrared shimmer shows where protostars are heating their surroundings, and the ultraviolet and X-ray notes reveal where they are clearing away the remnants of their birth clouds. Together, they compose the soundless symphony of the bubble's living edge. The Taurus molecular cloud is one of the most vivid examples. Spanning about 450 light-years from Earth, it forms part of the local bubble's eastern boundary. Within its dark filaments, hundreds of protostars are in various stages of formation. Some have already emerged as young T-Tauri stars, their stellar winds carving small cavities in the gas around them. Others remain deeply embedded, detectable only through the faint glow of their circumstellar disks. These disks, rich in dust and ice, are where planets are beginning to form. Every grain of material there is a fragment of the galaxy's recycled matter, drawn from the same gas that once filled the bubble's interior before being swept outward by supernova shockwaves. The young stars of Taurus are literally built from the debris of the explosions that made our cosmic neighbourhood. To the south, the Ophiuchus and Lupus clouds show similar scenes. Dense knots of gas collapse under their own weight, forming clusters of newborn stars surrounded by nebulae faintly glowing in infrared light. Observations from the Spitzer and Herschel space telescopes reveal bubbles within bubbles, smaller cavities inside the larger one, each created by the winds of new stars. These small-scale structures echo the same pattern that created the local bubble itself, repeating the cycle on a smaller stage. As the young stars grow, they inject energy back into the surrounding medium, sculpting it and preparing it for the next generation. The edges of the local bubble are not static walls, they are living boundaries, constantly reshaped by the interplay of creation and erosion. Astronomers studying these processes sometimes describe the local bubble as breathing. The term is poetic but accurate. The energy flowing from the interior to the boundary, the cooling and heating of gas, the cycles of compression and expansion, together they resemble the slow respiration of a living organism. Over millions of years, the bubble expands slightly as the hot plasma inside exerts pressure, then contracts as it cools and the outer regions thicken. The overall structure remains stable, but within it, energy and matter circulate. Stars born along the edges add new winds and radiation that alter the balance again. The bubble is both a product and a participant in the galaxy's metabolism, part of the system that regulates the Milky Way's temperature, density and brightness. The light that escapes from these edge regions is faint, but sensitive instruments can trace its movement. Ultraviolet observations reveal regions of ionized hydrogen, where the radiation from newborn stars has stripped electrons from atoms. These ionized zones outline cavities within the molecular clouds, small glowing hollows where star formation has begun. Infrared surveys show warm dust surrounding those hollows, heated by the same radiation. In some places, such as near the Perseus cloud, astronomers can see expanding shells within the larger boundary, evidence of ongoing interactions between the new stars and the old structure. The local bubble is literally reshaping itself through the light its edges produce. The breathing of light also happens through reflection. Dust grains along the bubble's shell scatter starlight from both the interior and the exterior, producing a diffuse glow known as the diffuse galactic light. This glow is so faint that it can only be seen with sensitive instruments under the darkest conditions, but it surrounds us on all sides. It is the visible counterpart of the X-ray and radio emissions that define the bubble's presence in other wavelengths. The galaxy is not a dark vacuum but a softly illuminated haze, and the local bubble is one of the brightest contributors to that background. Its boundaries act as a vast mirror, catching and redistributing starlight across hundreds of light years. As astronomers have refined their maps of the bubble, they have discovered more evidence of how deeply intertwined it is with nearby structures. The Gould Belt, a ring of young stars tilted relative to the galactic plane, coincides almost exactly with the local bubble's surface. For decades, the Gould Belt was a mystery, its origin uncertain. Now it's understood as the visible trace of the same process that shaped the bubble. The chain of supernova that swept through this region compressed gas into a ring that continues to form stars today. The belt's tilt matches the bubble's orientation, suggesting they are parts of a single, coherent system. The light from those young stars is the breath of the bubble made visible across the sky. Even the sun's current environment reflects this breathing cycle. The solar system moves through the thin remnants of gas inside the cavity, encountering variations in density and magnetic field that subtly alter the heliosphere's shape. Cosmic rays from the edges occasionally spike, hinting at distant disturbances. Though these changes are imperceptible to us in everyday life, they are reminders that our calm region of space is part of an active, evolving structure. The bubble's breath reaches us as faint ripples of energy, slow exhalations of the galaxy's vast respiration. What makes the local bubble so extraordinary is that we can observe this process from the inside. Most other bubbles and superbubbles in the galaxy are seen from afar, projected as glowing arcs against the background. Ours is unique because we are within its walls, surrounded by its glow on all sides. Every observation we make of the nearby interstellar medium, every map we build of dust and gas, is filtered through its geometry. Its breathing shapes the radiation that reaches us, the clarity of our view, and even the way we interpret the Milky Way structure. The bubble is not just a background feature, it is the stage on which we observe the universe. In time, the balance will shift again. The young stars along the edges will evolve, some eventually growing massive enough to explode as supernovae themselves. When that happens, new shockwaves will sweep through the existing shell, merging with the remains of the old structure and carving new cavities. The local bubble, as we know it, will become part of a new superbubble or collapse into a denser region, its identity lost in the next round of galactic change. But until then, its edges will continue to glow, nurturing the cycle of light it began millions of years ago. For now, the local bubble breathes gently, its boundaries shimmering with the light of newly born stars, its interior filled with the faint warmth of ancient fire. The light from those edges travels across hundreds of light years, crossing the empty interior to reach us. Every photon is a pulse of that slow respiration, a trace of energy exchanged between destruction and creation. And as we detect those photons, as we map their origins and measure their spectra, we are watching the galaxy itself breathe. When the idea first appeared, it sounded more like a guess than a revelation. The notion that our solar system might be floating inside a vast, invisible cavity in the galaxy, one carved out by ancient explosions, was difficult to confirm. Space is mostly empty. How do you prove that a particular kind of emptiness surrounds you? Yet over the decades, through patient observation and layers of indirect evidence, astronomers have managed to do exactly that. They have built, piece by piece, a portrait of the space we inhabit. Today we can say with confidence that the sun, the planets, and everything we know sit within the local bubble, a 1,000 light-year-wide cavity of hot, rarefied gas. The evidence doesn't come from a single discovery, but from an accumulation of clues, each one faint, each one pointing to the same conclusion. The first hints emerged from how starlight behaved. When light from distant stars passes through the interstellar medium, dust and gas alter it in predictable ways. Dust scatters blue light more than red, causing stars to appear redder than they truly are, a phenomenon called interstellar reddening. Gas, meanwhile, leaves sharp absorption lines in a star's spectrum, specific wavelengths that are blocked by elements like sodium or calcium along the way. By comparing spectra of stars at known distances, astronomers can measure how much matter the light has passed through. In most directions, the more distant a star, the greater the reddening and absorption. But for stars near the Sun, within a few hundred light years, this pattern suddenly drops off. The light is too clean, the absorption too low. It's as though the stars closest to us are shining through an unusually transparent patch of the galaxy. That patch, mapped in every direction, revealed itself as a roughly spherical void, the first outline of the local bubble. Even so, early maps were crude. Distances to stars were uncertain, and the structure of interstellar dust was poorly known. It wasn't until space-based telescopes began observing in ultraviolet and X-ray wavelengths that the picture started to sharpen. In the 1970s, detectors on satellites picked up a diffuse X-ray glow spread across the entire sky. It wasn't concentrated around any particular source, and its spectrum suggested temperatures near 1,000,000 degrees, far hotter than the typical interstellar medium. At first, astronomers thought the glow might come from distant quasars or the galactic halo, but careful analysis showed that some of it must originate nearby. The intensity of the emission correlated inversely with the amount of interstellar absorption. Where there was less dust, the X-rays were stronger. That correlation implied that the X-rays came from a hot, low-density gas surrounding the solar system itself. The idea took shape gradually. Astronomers realized that they were detecting the faint radiation of million-degree plasma filling a cavity in the local interstellar medium. The lack of dust and the presence of X-ray emitting gas could both be explained by the aftermath of multiple supernovae that had swept the region clean millions of years earlier. As the data accumulated from satellites like Rosat, XMM Newton and later Erosita, the map of that diffuse X-ray background grew increasingly detailed. Its brightness varied across the sky, stronger in some directions, weaker in others, matching the irregular shape of the local bubble inferred from optical data. Another line of evidence came from the polarization of starlight. Dust grains tend to align with magnetic fields, and when light passes through them, it becomes polarized. Its waves oscillate preferentially in one direction. By measuring the polarization of light from many nearby stars, astronomers can trace how the galactic magnetic field bends and twists through space. The resulting patterns revealed a curious curvature, field lines wrapping around an empty cavity centered near the Sun. The polarization data showed the magnetic skeleton of the local bubble, invisible in ordinary light but unmistakable in its influence on starlight. Radio observations added yet another perspective. Neutral hydrogen, the most abundant element in the interstellar medium, emits radio waves at a wavelength of 21 centimeters when its electron flips its spin relative to its proton. By mapping this emission, astronomers can chart where neutral gas lies and how dense it is. Surveys of hydrogen in our region show a conspicuous hole around the Sun, surrounded by denser concentrations in every direction. It is as if the ordinary sea of interstellar hydrogen has been drained here, leaving behind a cavity bordered by clouds, the same clouds visible in optical and infrared maps. As data from different wavelengths converged, the concept of the local bubble transformed from hypothesis to fact. But even with this evidence, the precise shape and size of the cavity remained elusive until recently. The revolution came with the Gaia mission. Launched in 2013, Gaia measures the positions, motions and distances of more than 1 billion stars with unprecedented accuracy. For the first time, astronomers could build a true three-dimensional map of the local interstellar medium by combining Gaia's distances with measurements of starlight reddening. Each star acts as a probe, its colour and brightness revealing how much dust lies between it and the Sun. By assembling data from millions of such probes, researchers reconstructed a volumetric picture of dust density surrounding us. The results were striking. Instead of an even distribution, the dust forms a complex network of filaments and voids. At the centre lies a broad, irregular cavity devoid of dense material, the local bubble. Its boundaries correspond almost exactly to known molecular clouds like Taurus, Perseus, Ophiuchus, and Chamaeleon. When the maps are rendered in 3D, the structure looks like a hollow tunnel, elongated along the galactic plane and tilted relative to it. The Sun sits near its centre, slightly offset from the geometric middle but well within its boundaries. The alignment between the dust maps, X-ray data, and star-forming regions leaves little doubt. This is our home cavity, the product of multiple supernovae and the environment through which the solar system now drifts. One of the key insights from Gaia's data is that the local bubble is still expanding, albeit slowly. The young stars along its surface, particularly those in the Gould Belt, show motion consistent with having been pushed outward from the cavity's centre. By measuring their velocities, astronomers can estimate when the expansion began. The results point to a series of explosions starting about 14 million years ago, and continuing until 2 or 3 million years ago, exactly the timescales inferred from isotopic evidence on Earth. This consistency across independent lines of research, spectroscopy, X-rays, magnetism, radio waves, isotopes and stellar motion, makes the case overwhelming. We are, without question, inside the relic of an ancient chain of supernovae. Even with such strong evidence, refining the details remains an ongoing challenge. The boundary of the bubble is uneven. In some directions it merges with neighbouring cavities, like the Lupus bubble and the Orion Eridanus superbubble. Distinguishing where one ends and another begins requires high-resolution data and complex modelling. Instruments like eROSITA, with its ability to map the X-ray sky in exquisite detail, are helping astronomers trace the exact contours of the hot plasma inside. Combining those results with Gaia's dust maps yields a layered view of the cavity, revealing how its interior gas overlaps with the cooler shells at its boundary. The discovery that the local bubble's edges host nearly all nearby star-forming regions came as one of the most surprising outcomes of this research. It showed that the bubble's influence is not just historical but ongoing. The same structures that mark its boundaries are actively shaping the next generation of stars. The connection between the bubble's expansion and the creation of new stellar nurseries provides a vivid demonstration of how galaxies recycle energy. By studying our immediate environment, we can watch that process unfold up close. There is even evidence that the sun's position inside the bubble affects what we can observe of the larger universe. Because the region is so clear of dust, light from distant stars reaches us with minimal interference. That transparency has allowed astronomers to measure more distant objects in detail, effectively giving us a cosmic window through which to study the Milky Way. If the Sun were located inside a dense molecular cloud instead, the night sky would appear dimmer, and much of the galaxy's structure would be hidden from view. The clarity of our sky is, in part, a result of our position within this vast void. The process of confirming that we live inside the local bubble has also deepened our understanding of the galactic environment more broadly. Similar cavities have been identified elsewhere in the Milky Way, each associated with clusters of massive stars and supernova remnants. The study of these bubbles has shown that they often connect, forming a network of tunnels that span the galactic disk. The local bubble is simply one of many such cavities, though it happens to be the one we can explore from within. Its detailed mapping serves as a template for interpreting others. Perhaps the most compelling part of this discovery is its perspective. For most of human history, we imagine space as a void between stars, a blank nothingness. What we've learned instead is that even emptiness has structure. The space surrounding us is not uniform but shaped by energy and time. Every patch of the galaxy has its own texture, its own story. The local bubble is ours, a hollow sculpted by fire cooled into peace and illuminated by the faint light of new beginnings. The knowledge that we live inside such a structure changes how we see the sky. The bright arc of the Milky Way overhead is no longer a distant abstraction. It's a cross-section of the environment that holds us. The dark lanes are not empty gaps, but the outlines of the walls that form our boundary. The faint X-ray and infrared glows that instruments detect are not background noise. They are the ambient breath of our galactic home. Every observation we make of the cosmos passes through this medium, carrying its signature. And yet, for all the data we've gathered, there's a certain humility in realizing that we discovered this structure only recently, and only by inference. We cannot step outside to see it directly. We piece it together from the light of others, from shadows and glows and magnetic whispers. That is the essence of astronomy itself, understanding vast realities through faint traces of light. We know we are inside the local bubble because the universe has left us just enough evidence to read its story. The fact that we live inside a vast bubble of hot, thin gas might seem like an abstract curiosity, the kind of detail that belongs in an astronomy textbook rather than in the story of our own existence. But the local bubble is not a remote feature of the galaxy. It is the environment that surrounds us. It shapes the light that reaches Earth, the radiation that moves through our skies, and the long-term stability of the space we inhabit. We are not separate from it. We are inside it, and its quiet boundaries define what here means in cosmic terms. To understand what the bubble means for us, we have to see how deeply it is woven into the conditions that make our planet what it is. Our solar system drifts through the interior of the local bubble at about 20 kilometers per second, carrying with it the bubble within the bubble, the heliosphere, created by the solar wind. The heliosphere is a vast, invisible shell of charged particles streaming outward from the sun. It forms a protective barrier that shields the planets from most of the high-energy cosmic rays that fill the galaxy. How large and strong that barrier is depends on the pressure of the interstellar medium around it. In denser regions, the heliosphere is compressed, the solar wind pushed back by external gas and magnetic fields. Inside the local bubble, where the interstellar density is 100 times lower than average, the heliosphere can expand freely. It extends far beyond the orbit of Pluto, perhaps twice as large as it would be in a denser environment. That difference matters. A larger heliosphere provides a thicker shield against galactic cosmic rays. Those energetic particles can penetrate atmospheres and interact with planetary climates. On Earth, they produce secondary particles in the atmosphere that influence ionization rates and can affect cloud formation. On biological scales, they can alter mutation rates and radiation exposure. A quiet interstellar environment, like the one provided by the local bubble, means fewer cosmic rays, more stability, and a gentler background for life. It is possible that the Earth's long periods of climatic stability owe something to this quietness, a byproduct of being sheltered in a region of low-density gas. It is not that the bubble was designed for us, but that life evolved under the conditions it provided. The calm of the local bubble has been part of Earth's context for millions of years. The bubble's emptiness also influences what we can see. Because there is so little dust between us and the stars, the sky appears unusually clear. Starlight passes through the cavity almost unimpeded, allowing us to observe distant parts of the galaxy in visible and infrared light. If the sun were inside a dense cloud, the Milky Way would look dimmer, redder, and more obscure. The transparency of our surroundings is the reason astronomy has been possible as we know it. It is as though the galaxy placed us in a cosmic window, a rare vantage point where we can see both inward toward its crowded heart and outward toward the quiet halo beyond. The local bubble's clarity is the lens through which we discovered the structure of the universe. For all its quiet, the bubble also serves as a reminder of violence. Every atom of gas that fills it was once part of a storm of unimaginable power. The empty space we inhabit was created by destruction, and yet from that destruction came conditions suitable for stability and life. That paradox, the idea that calm can arise from catastrophe, is written into the very matter around us. The local bubble is both a scar and a shelter, the lingering imprint of energy long spent. It teaches us that even the most violent forces in the cosmos eventually give way to peace, and that the boundaries between chaos and order are not fixed but cyclical. This connection between violence and creation extends to our own planet's origins. The heavy elements that make up Earth, the iron in its core, the silicon in its crust, the oxygen we breathe, were forged in supernovae, like those that created the local bubble. The same class of stars whose deaths hollowed out our region also seeded it with the materials for future worlds. When the sun formed 5 billion years ago, it condensed from gas already enriched by countless previous explosions. The local bubble represents one iteration of that ongoing process. Its edges, now forming new stars, will one day give birth to planets that contain the remnants of our present era. The cycle continues endlessly. Stars die, space clears, new stars are born from the debris. We are both the product and the witness of that rhythm. The conditions inside the bubble affect not only Earth, but the entire solar system. As the sun moves through the interstellar medium, the changing density and magnetic fields outside influence the heliosphere's shape. These variations subtly modulate the flow of cosmic radiation entering the solar system. Over geological timescales, such changes may leave fingerprints in the Earth's climate record. When the solar system eventually leaves the local bubble, something that may happen a few million years from now. It will enter a region of higher density. The heliosphere will contract, cosmic rays will increase, and the background environment will shift. For future life on Earth or any descendants of it elsewhere, that transition will mark a change in the cosmic weather. The calm we enjoy now will not last forever. Even the night sky as we know it owes something to our location within this cavity. The distribution of nearby dust and gas affects how light scatters, how stars twinkle, and how interstellar clouds frame the Milky Way's band. The crisp brightness of the constellations, the clean contrast between the dark sky and the galactic glow, all of it depends on the bubble's transparency. We are surrounded by clarity not because space is empty, but because it has been cleared by time and energy. The local bubble acts like a cosmic observatory, a naturally occurring window into the deeper layers of the galaxy. Every telescope on Earth and in orbit benefits from that transparency, though we rarely acknowledge it. The local bubble also gives us perspective on scale. The distances involved are so large that the entire solar system, from the Sun to the outermost comet, occupies less than a single pixel in a full map of the bubble. The cavity that defines our environment could contain billions of planetary systems like ours, and yet within that immensity conditions are delicately balanced. A thin plasma at 1,000,000 degrees, a faint X-ray glow, and a web of magnetic fields stretching across hundreds of light years. To live inside such a structure is to exist within an intersection of scales, the human, the planetary, and the galactic, all overlapping in the same physical space. For astronomers, the local bubble is a laboratory. Its boundaries are close enough to study in detail, allowing scientists to observe how interstellar gas transitions from hot to cold, how magnetic fields shape those transitions, and how stars form along compressed fronts. It provides the nearest example of a super bubble environment, a kind of structure that dominates the disks of spiral galaxies. Understanding it helps researchers model the larger processes that govern the Milky Way's evolution. The fact that we are inside it makes it both easier and harder to study. Easier because it surrounds us, harder because we can only view it from within, but it also gives us a sense of belonging. The local bubble is not just a subject of research, it is our cosmic address. In another sense, the bubble's existence reminds us of fragility. The calm we experience is temporary. Somewhere beyond our region, other clusters of massive stars are already forming, their future explosions destined to carve new cavities and reshape the galaxy's texture. The local bubble will fade, merge, or collapse, and the sun will move on. The stability it provides is measured not in eternity but in millions of years. For us, that's long enough to build civilizations, to evolve, to look outward and wonder. But in the galactic context, it's a pause between storms, and yet within that pause the conditions are perfect for reflection. To realize that our entire solar system floats inside the cooled remains of long-vanished supernovae is to feel both small and deeply connected. The airless vacuum beyond Earth's atmosphere is not an indifferent emptiness, but a record of energy spent, of creation and renewal intertwined. The local bubble is the silence after cosmic thunder, and we are the listeners inside it. Its meaning, then, is not just scientific, but existential. It shows that calm and chaos, life and death, light and darkness are all part of one continuum. The same galaxy that once filled this space with fire now uses that emptiness to cradle new light. The same void that could have been hostile has become a place of safety. In that sense, the local bubble is a metaphor written in physics, a demonstration that what looks like emptiness can be full of history, that what seems like stillness can be the balance point between vast opposing forces. Every night when you look up at the sky, you're seeing through that balance. The clarity of the stars, the depth of the Milky Way, the faint glow that lies between, these are the visible expressions of the bubble's quiet. The space we move through is not nothing. It is the lasting calm left behind by a chain of dying stars, and for a moment in cosmic time, We get to live inside it, to study it, and to understand that our existence, every breath, every thought, takes place inside the gentle heart of a storm long gone. If the sun could leave a trail behind it, a glowing line that traced its motion through the galaxy, we would see that it has spent only a small fraction of its life inside the local bubble. For most of its billions of years, it has drifted through regions of ordinary interstellar gas, places filled with dust, dense clouds, and the quiet glow of hydrogen. The bubble is only a chapter in that longer journey, a temporary refuge carved out by forces that existed long before we arrived. Eventually, that journey will carry the solar system beyond the bubble's walls. The space beyond is not hostile, but it is different, denser, cooler, and more complex. What lies ahead is the rest of the galaxy, waiting with its own variety of structure and rhythm. Leaving the local bubble won't be dramatic. The sun's motion relative to the surrounding gas is slow enough that the transition will unfold over hundreds of thousands of years. The heliosphere, the vast bubble created by the solar wind, will gradually adjust as the pressure outside it increases. The boundary where the solar wind meets interstellar gas will shrink, bringing the influence of the galaxy a little closer. The density of neutral hydrogen will rise, the temperature will drop, and the number of cosmic rays reaching the solar system may climb. None of this will happen abruptly. The change will be gradual, smooth, and undetectable on human timescales. But across the immense span of cosmic time, the difference will matter. The interstellar space beyond the bubble is not uniform. It's a landscape of clouds and gaps, of filaments where gas has cooled and condensed, and pockets where energy still lingers from ancient shocks. The nearest of these features may already be visible at the bubble's edges: the Taurus molecular cloud, the Ophiuchus complex, the Chamaeleon clouds, and countless smaller fragments. They form the boundary that separates the clear interior from the opaque outer galaxy. When the sun eventually crosses that boundary, it will move into a region where dust dims the light of distant stars, and where the heliosphere contracts under the weight of denser gas. The surrounding conditions will shift from the serenity of low-density plasma to the slow, granular motion of interstellar clouds. Astronomers have tried to imagine what this transition would mean for a planet like Earth. The changes in cosmic ray flux and interstellar density could alter the upper atmosphere and the balance of radiation that reaches the surface. Some researchers have even speculated that such changes might influence long-term climate cycles, though the evidence remains uncertain. The larger truth is simpler. The solar system's environment is not fixed. It evolves as the sun moves, and that motion connects our local history to the larger flow of galactic evolution. Each region we pass through carries its own history, its own echoes of the stars that shaped it. The space beyond the local bubble is also home to other cavities, other relics of long-past explosions. The loop-up bubble lies adjacent to ours, formed by supernovae in the same Scorpius-Centaurus association that built our own cavity. The two structures overlap, connected by channels of thin gas through which hot plasma flows. On the far side of the loop-up bubble lies the North Polar Spur, a vast arc of emission stretching high above the galactic plane. Together, these features form part of a complex network of voids and shells that extends for thousands of light years. The local bubble is simply one cell in this cosmic foam, and the space beyond its boundary is another cell waiting to be entered. As the sun continues its slow orbit around the galaxy, it will eventually pass from one cavity to the next, then perhaps into denser regions where clouds collapse and new stars are born. The journey will take millions of years, each phase offering a new environment. To us, it will seem like continuity. The same dark sky, the same band of the Milky Way overhead, but the details will shift. The background glow of X-rays may fade as we move into cooler gas. The distribution of dust will change, altering the colours of starlight. Over even longer times, new constellations will form as the sun's neighbours drift away, and others take their place. The night sky will never be static. It's a living record of motion through the galaxy structure. The boundaries between bubbles like ours are not rigid. They expand, merge, and collapse as energy moves through the interstellar medium. When two cavities meet, their walls can rupture, allowing hot gas to escape and cooler gas to flow in. Over time, the differences between them blur, and the larger structure becomes a single, more complex region. The local bubble may already be in such a phase. Its openings toward the loop or bubble suggest that it's not isolated but connected to a broader superbubble complex. As those links widen, the identity of the local bubble will dissolve, replaced by a larger merged cavity. The calm interior we experience today will gradually become part of a new equilibrium, shaped by the overlapping histories of many clusters of stars. This process, of bubbles expanding, colliding, and merging, is one of the key mechanisms by which the galaxy evolves. Each generation of massive stars injects energy into the disk, carving out new voids. Over millions of years, these voids link together into a web that channels gas and dust into certain regions while leaving others clear. The result is the Milky Way's textured appearance: patches of brightness and darkness, filaments of gas connecting distant regions, and networks of star-forming clouds aligned along the edges of cavities. Our journey beyond the local bubble will carry us through that web, through the galaxy's vast and ever-changing architecture. In that sense, there is no true outside of the bubble, only the continuation of the same process on a larger scale. The space beyond is not a different kind of medium, but the same interstellar matter at a different point in its cycle. The boundaries we describe are simply places where the balance of energy shifts from hot to cold, from expansion to compression. Once the sun crosses the bubble's edge, it will enter another region shaped by a different history of explosions and collapses. Every part of the galaxy has been sculpted by such events. The Milky Way's disk is like a tapestry woven from the overlapping lives of stars, each thread representing a burst of energy or a flow of gas. The local bubble is one of those threads, and moving beyond it means following the weave onward. From our perspective, though, the idea of leaving the bubble carries a sense of change. For all its invisibility, the local bubble has become a kind of conceptual home. We've mapped it, measured it, and learned to see its shape in the patterns of light that fill our sky. To imagine moving beyond it is to imagine the next stage of the galaxy's evolution, one in which the calm we now enjoy gives way to new dynamics. If another cluster of massive stars were to form near the edge of our region, their eventual deaths could ignite new shockwaves, refreshing the cavity or replacing it entirely. In a galaxy as active as the Milky Way, such events are inevitable. And yet there's something comforting in knowing that the bubble story continues elsewhere. Every part of the galaxy contains its own version of this process. Pockets of calm surrounded by shells of creation, regions cleared by death only to give rise to new light. The local bubble is not unique. It is one cell in the galaxy's living structure, one breath in its endless respiration. Beyond its boundaries lies more of the same rhythm: expansion, cooling, renewal, repeating across millions of light years. For us, the significance of what lies beyond is less about danger or safety, and more about continuity. The sun will keep moving, the galaxy will keep breathing, and new bubbles will form as old ones fade. The path ahead is not an exit, but a continuation of the same process that brought us here. The universe has no hard edges. Everything flows into everything else. From the vantage point of Earth, the journey beyond the bubble is invisible, unfolding too slowly to notice. But it is happening even now. The solar system glides through the thin plasma at the center of the cavity, inching toward its next environment. Long after our species is gone, long after the Earth itself has changed beyond recognition, the sun will still be moving through the galaxy, carrying the memory of this quiet region within it. The traces of the local bubble will persist in the distribution of dust and gas, in the stars that formed along its rim, and in the faint X-ray glow that marks where ancient energy once filled space. To imagine what lies beyond is to understand that the galaxy has no boundaries except those we draw for convenience. The local bubble is not an isolated phenomenon, but a glimpse of how energy and matter circulate through the Milky Way. The spaces beyond it are not foreign. They are family, connected by the same flows that shaped our home, and as the Sun continues its long orbit, it will pass from one of those spaces to another, always within the same grand pattern, always inside the living fabric of the galaxy. That realization leads naturally to a deeper reflection. If we live inside one of the galaxy's countless bubbles, and if each of those bubbles connect to others, then the Milky Way itself is a single, breathing organism. Its stars, the cells, its gas, the bloodstream, its supernovae, the pulse. Beyond our local region lies not emptiness, but the continuation of that pulse, the wider heart of the galaxy beating around us. The local bubble is a quiet chamber in that heart, and as we drift toward its edge, we do so as part of a rhythm that began long before us and will continue long after we are gone. And perhaps, as we look beyond, what we're really seeing is not departure but perspective. To move beyond the bubble is to recognise that our home is not defined by boundaries of gas or dust, but by our understanding of how those boundaries form and fade. The space ahead, like the space behind, is part of the same cosmic breath, the same slow inhalation and exhalation of energy that shapes every star, every planet, every world capable of looking up and wondering where it lives. If you look up tonight and let your eyes rest on the darkness between the stars, you are looking through the centre of the local bubble. The space between you and those distant points of light isn't empty. It's the thin, glowing breath of the galaxy, stretched across hundreds of light years, silent and clear. Every photon that reaches your eyes has passed through the same invisible cavity that holds our sun, our planets, and all that we call home. The local bubble doesn't announce itself. It has no visible edge or border. It is simply there, a quiet openness that has existed for millions of years, the lingering calm after storms that ended before there was even an Earth to witness them. This place we live in, the quiet interior of a galactic hollow, is more than an astronomical curiosity. It is the setting of everything we know, the space that allows starlight to pass so clearly, that keeps the solar wind extended and the heliosphere wide, that shelters us from much of the galaxy's radiation, is the legacy of long-gone stars. Every gentle night, every tranquil dawn, is framed by that history. The stillness that fills the solar system is not primordial, it is inherited. The calm we call normal was brought by the energy of massive stars that lived and died millions of years ago, their deaths sculpting this region into a refuge of light and quiet, the faint X-rays that fill the sky, the clean transparency of starlight, the soft ultraviolet shimmer that instruments detect in every direction. All of it is the background breath of that inheritance. It is a soundless echo of the past, the afterglow of explosions that once filled this region with shockwaves and heat. Over time, those shockwaves faded, the gas cooled, and the chaos subsided into equilibrium. What remains is balance, pressure holding against gravity, light scattering gently through dust, stars forming at the edges where the old energy condensed into new creation. We live in that balance. There's a kind of comfort in realizing that even something as vast as a galaxy can hold stillness. Between the arms of the Milky Way, between the density waves that trigger new generations of stars, there are gaps, interludes of quiet where energy diffuses and space becomes clear. The local bubble is one of those interludes. It is a pause in the galaxy's restless motion, a space where calm and creation coexist. From within it, the stars appear sharper, the distances cleaner, the boundaries of the universe easier to imagine. We look out from a rare moment of clarity, suspended inside a structure built from fire and preserved by peace. If we could see the bubble directly, not through data but with our own eyes, it would appear as a faint shell around the solar system, glowing softly in invisible light. Beyond it, clouds of gas and dust would drift like mist, the edges of Taurus and Perseus lit by newborn stars. The sun would sit near the centre, its light mingling with the diffuse glow of the cavity. In every direction, faint filaments of magnetized gas would trace the history of ancient supernovae. It would look serene from afar, almost delicate, yet it spans hundreds of light years and contains the energy of 1,000,000 suns once spent in a single breath. From Earth, that structure feels abstract because it's too large to experience, but its effects touch every moment of our lives. The clarity of our atmosphere, the brightness of the night sky, even the steady conditions that have allowed life to persist, all are shaped by our position within this bubble. The radiation that reaches our planet is filtered through layers of protection: the heliosphere, the bubble's low-density plasma, and the magnetic fields that stretch across the galactic disk. Together they form a kind of cosmic insulation, not perfect, but enough to soften the extremes of space. The Earth exists in the quiet heart of that insulation, a planet orbiting inside the relic of a long-vanished storm. There's a humility in knowing that. For centuries humanity looked outward and saw a universe of stars without context. We imagined space as endless emptiness, a void between points of light. Only recently have we learned that even the void has a history, that the emptiness itself is shaped by time and energy, by creation and destruction. The local bubble is a reminder of that truth. It is a structure made of absence, a place defined not by what is there but by what is missing. And yet, in that missing matter lies a record of everything that came before. It's the memory of light in a medium that once burned and now rests. To live within it is to occupy a kind of cosmic calm. We are surrounded by the remnants of events that could have destroyed worlds, yet we experience them only as stillness. The quiet is not the absence of energy, but its equilibrium. The same physics that once drove shockwaves through this region now holds it in gentle balance. The stars born at its edges shine softly through its transparency, their light crossing hundreds of light years to touch our eyes. In that light is history, ancient, invisible, and ongoing. The local bubble is temporary, of course. The galaxy is always moving, always changing. In a few million years, the sun will drift out of this cavity into denser gas, perhaps into a new region shaped by other supernova. The quiet will end, replaced by another kind of equilibrium. But for now, we exist in a moment between storms. The energy of the past has spent itself, and the energy of the future has not yet begun. The calm between those two states is where we live, where we think, where we observe. It's where we dream about the rest of the galaxy, unaware that the clarity through which we see it is itself a product of that same galaxy's breath. If you close your eyes and imagine the Milky Way as a living system, its arms rotating, its stars burning and dying, its gas pulsing between heat and cold, you can imagine the local bubble as one of its quiet heartbeats. We happen to exist within that heartbeat, in the interval between one pulse and the next. The stillness we feel is not isolation, it's participation in the galaxy's own rhythm. Every photon of light we see, every cosmic ray that passes through us, every magnetic line threading space is part of that same movement. We're inside the galaxy's pores, carried gently in its ongoing respiration. When the night grows dark and the stars begin to shimmer, it's easy to forget how unlikely it is that we can see them so clearly. The view above is possible because we are looking outward from a rare vantage, a clear bubble carved by violence, polished by time, and left open for us to inhabit. The faint glow of starlight on the edge of the Milky Way is the soft reflection of our galactic home. We live inside that glow, warmed by its calm, shielded by its emptiness, surrounded by the invisible memory of creation. And as the earth turns beneath that glow, as night gives way to morning, we remain in that same place, in the quiet heart of the galaxy's long exhalation. The storms have passed, the light has settled, and what's left is balance. The local bubble continues to drift, vast and unseen, carrying us with it. It is the soft shell of our existence, the silent architecture of the space between stars, the calm cradle of a restless universe. That is our address in the Milky Way. Not a point marked by coordinates, but a region of peace held open by the memory of light. We're inside the bubble now, wrapped in its quiet, watching the stars through its transparent skin. And somewhere, far beyond its edge, the next generation of suns is forming, preparing to light the galaxy anew. For this moment, though, we remain here, suspended in stillness, surrounded by the soft glow of home.